What if we were not the first? This question haunts the edges of scientific inquiry, challenging our most fundamental assumptions about humanity's place in Earth's vast timeline. Tonight, we embark on a journey through deep time, exploring one of the most provocative hypotheses in modern science, the possibility that industrial civilizations may have risen and fallen on our planet millions of years before humans ever existed. The very ground beneath our feet tells a story, but it's a story with missing chapters, torn pages, and entire volumes lost to the relentless forces of geological time. Earth is both a keeper of secrets and their destroyer, preserving some traces of the past while erasing others with stunning efficiency. If ancient civilizations once thrived on our world, their evidence might be hidden in ways we're only beginning to understand, or it might be gone forever, leaving us to wonder about ghosts that may never have existed at all. This is not a tale of ancient astronauts or lost continents. This is rigorous science grappling with extraordinary possibilities. It's the story of how two respected scientists dared to ask what everyone assumed was an impossible question, and in doing so, opened a new window into Earth's deep past and our own future. Introduction. The unsettling question. Picture this. You're standing in a museum, gazing at a dinosaur skeleton from the Cretaceous period, 66 million years ago. The bones are real, ancient, testament to life's incredible persistence through deep time. But here's what's unsettling: between that T-Rex and the first human civilization lies a span of time so vast that our entire recorded history represents less than 0.1% of it. In that enormous gap, Earth experienced ice ages, mass extinctions, the rise and fall of countless species, and climate changes that dwarf anything in human experience. Now consider this uncomfortable fact. If our current industrial civilization were to vanish tomorrow, what traces would remain after just 1 million years? Our cities would crumble and be buried. Our plastic would eventually break down. Our metals would oxidize and scatter. Even our nuclear waste, seemingly eternal, would decay to barely detectable levels. The busy, noisy, technological world we've built might leave less evidence of its existence than a single dinosaur bone. This isn't pessimistic speculation, it's the stark reality of geological time. Earth is ancient beyond human comprehension, and it's been very busy during those billions of years. The planet's surface has been recycled countless times through plate tectonics. Mountains have risen and been worn to nothing. Entire ocean floors have been swallowed by subduction zones. The climate has swung from hothouse to icehouse and back again, multiple times. The fragility of Earth's geological memory becomes apparent when we consider what we can actually observe from the deep past. We have exquisite fossils of creatures that lived hundreds of millions of years ago, yet we have virtually no direct evidence of Earth's surface conditions from just a few million years ago. We can tell you about the anatomy of a trilobite from 500 million years ago, but we struggle to reconstruct the exact geography of North America from 5 million years ago. This erasure is not uniform or predictable. Some things preserve beautifully: a delicate leaf impression in limestone, a dinosaur footprint in mudstone. Others vanish without a trace: entire forest ecosystems, vast migrations of animals, even mountain ranges that once rivaled the Himalayas. The geological record is like a vast library where most of the books have been lost, and the remaining ones have pages missing, paragraphs smudged, and entire chapters torn out. Yet it's precisely this imperfection in the record that opens up space for extraordinary possibilities. If Earth's geological memory is so fragile, so selective in what it preserves, then we must seriously consider what might have been lost, not in the spirit of wild speculation, but as a matter of scientific rigor. When the evidence is absent, We cannot assume absence of the phenomenon, we can only acknowledge the limits of our knowledge. The question, what if we were not the first, isn't born from arrogance or a desire to diminish human achievement. It emerges from a profound appreciation of deep time and a recognition that Earth's story is far stranger and more complex than we often assume. This question forces us to confront our assumptions about progress, about the uniqueness of intelligence, and about our planet's capacity to both preserve and destroy the evidence of its own history. Throughout this exploration, we'll maintain the delicate balance between scientific curiosity and scientific rigor. We're not searching for evidence of ancient astronauts or lost Atlantean civilizations. We're asking what legitimate traces a genuinely ancient industrial civilization might leave behind, and whether we would recognize those traces if we found them. We're exploring the boundary between the possible and the probable, guided by the best current understanding of geology, climatology, and the nature of technological civilizations. This journey will take us through concepts that challenge our intuition about time, about civilization, and about our own significance in the cosmic story. We'll discover that the question of ancient civilizations is ultimately a question about the future, about what traces our own civilization might leave, about the patterns that technological societies might follow, and about the long-term prospects for intelligence on Earth and beyond. The unsettling question we're exploring tonight is not just about the past, it's a mirror held up to our own civilization, forcing us to think deeply about what it means to leave a lasting mark on a planet that specializes in forgetting. The scale of deep time. To truly grasp the possibility of lost civilizations, we must first confront something that human minds are not well equipped to understand: the sheer immensity of Earth's history. We live our lives in scales of days, years, perhaps decades. Our recorded history spans mere millennia. But Earth has been spinning through space for 4.5 billion years, a number so large it becomes almost meaningless until we find ways to visualize it. If Earth's entire history were compressed into a single year, multicellular life wouldn't appear until November. Dinosaurs would rule for only the last week of December. Human civilization would begin in the final seconds before midnight on New Year's Eve. Our entire industrial age would flash by in the last millisecond. This isn't just a clever analogy, it's a humbling reminder of how recent we are, and how vast the stage is on which we're performing. But the scale of deep time is only part of the challenge. The other part is understanding how efficiently Earth erases its own history. Our planet is not a passive repository of information, it's a dynamic, active system that constantly reworks its surface through processes that operate on timescales ranging from seconds to hundreds of millions of years. Consider erosion, perhaps the most relentless force shaping Earth's surface. Every raindrop, every gust of wind, every freeze-thaw cycle slowly but steadily wears down the landscape. Mountains that took millions of years to rise are gradually ground down to sand and sediment. The Appalachian Mountains, once as tall as the Himalayas, have been worn down to gentle hills over hundreds of millions of years. Even the rocks that form the foundations of continents are not permanent, they too are slowly recycled through geological processes. Plate tectonics operates on an even grander scale. The Earth's crust is broken into massive plates that slide over the partially molten mantle beneath. These plates collide, creating mountain ranges and deep ocean trenches. They pull apart, creating new ocean floor and rift valleys. Most dramatically, they slide beneath one another in the process called subduction, carrying entire sections of the Earth's surface down into the planet's interior, where they're melted and recycled. This process is incredibly efficient at destroying evidence. The oldest oceanic crust on Earth is only about 200 million years old, young by geological standards. Everything older has been swallowed by subduction zones. Entire ancient oceans have disappeared without a trace, taking with them any evidence of what might have existed on their floors or shores. Even continental crust, which is more buoyant and harder to destroy, is constantly being reworked. Ancient rocks are metamorphosed by heat and pressure, erasing their original structures and compositions. They're intruded by molten rock from below, fractured by earthquakes, and weathered by surface processes. The oldest rocks on Earth, found in a few precious locations like the Canadian Shield, are over 4 billion years old, but they tell us almost nothing about surface conditions at the time they formed. The atmosphere and oceans add another layer of complication. Earth's climate has changed dramatically throughout its history, swinging between ice ages and greenhouse periods. During ice ages, glaciers scraped away vast amounts of surface material, carrying it to the sea and grinding up everything in their path. During greenhouse periods, higher sea levels flooded continental margins, burying surface features under layers of marine sediment. Even the composition of the atmosphere itself has changed radically over geological time. For most of Earth's history, there was little or no oxygen in the atmosphere. The oxygen we breathe today is largely a byproduct of photosynthesis by ancient bacteria and plants. This change in atmospheric composition would have profoundly affected the preservation of any artifacts or structures from the deep past. The extreme rarity of anything surviving millions of years intact becomes clear when we examine the fossil record. Despite billions of organisms having lived and died over Earth's history, fossils are exceptionally rare. The conditions required for fossilization, rapid burial in sediment, the right chemical environment, protection from erosion, occur in only a tiny fraction of cases. Most organisms simply decay and disappear, leaving no trace of their existence. This rarity is even more pronounced for surface features and structures. We have no buildings, no roads, no artifacts from millions of years ago, not because intelligent beings weren't there to build them, but because such structures would be incredibly unlikely to survive the constant reworking of Earth's surface. Even natural features like river channels, shorelines, and forest patterns are erased and replaced on much shorter timescales. The few things that do survive from the deep past are typically those that were buried quickly in sediment and then preserved in stable geological formations. A tree buried in volcanic ash might become a fossil. A shell buried in mud might mineralize and persist. But a city built on the surface, exposed to weather and erosion, would have essentially no chance of surviving intact for millions of years. This creates what geologists call a preservation bias. The things that survive from the deep past are not necessarily representative of what actually existed. We have an excellent record of marine organisms with hard shells because they're easily fossilized. We have a much poorer record of terrestrial organisms with soft tissues because they rarely preserve. Similarly, any ancient civilization's traces would be subject to these same preservation biases, making some types of evidence much more likely to survive than others. The deep time perspective also reveals something else important. Earth has experienced events and conditions with no modern analog. Asteroid impacts have periodically devastated the planet's surface. Massive volcanic eruptions have pumped enormous amounts of gas and ash into the atmosphere. The planet has been completely or nearly completely frozen during snowball Earth episodes. It has also experienced extreme greenhouse periods when crocodiles lived at the poles. These events remind us that Earth's past includes conditions far more extreme than anything in human experience. A civilization that arose during one of these unusual periods might have developed very different technologies and left very different traces than we would expect based on our own experience. The scale of deep time forces us to think differently about evidence and absence of evidence. In human affairs, if we find no evidence of something, we often conclude it didn't happen. But in geological time, the absence of evidence might simply reflect the efficiency with which Earth erases its own history. The question becomes not where is the evidence, but rather what kind of evidence might possibly survive such vast spans of time. This temporal perspective is crucial for understanding the Silurian hypothesis. When we ask whether ancient industrial civilizations might have existed, we're not asking whether their buildings and machines survived, they almost certainly didn't. We're asking whether any traces, however subtle, might have been incorporated into the geological record in ways that we might still detect millions or tens of millions of years later. What is a civilization? Before we can seriously explore the possibility of ancient civilizations, we must confront a deceptively simple question. What exactly do we mean by civilization? This isn't merely an academic exercise. How we define civilization determines what evidence we should look for and what traces such societies might leave behind. The word civilization comes from the Latin civilis, meaning of or relating to citizens. But this etymology reveals the first challenge in our definition. It implies cities, formal governance, and complex social organization. Yet this urban-centric view might be too narrow for our purposes. If we're searching for evidence of ancient societies, we need to consider the full spectrum of human organization and technological development. Traditional archaeological definitions of civilization typically include several key features: permanent settlements, social stratification, specialized occupations, monumental architecture, writing systems, and complex political organization. The classic examples: Mesopotamia, Egypt, the Indus Valley, ancient China, all exhibit these characteristics. But even these early civilizations show remarkable diversity in their expression of complexity. Consider the contrast between Mesopotamian cities, with their towering ziggurats and extensive cuneiform archives, and the Indus Valley civilization with its sophisticated urban planning but apparent lack of monumental architecture or deciphered writing. Both are unquestionably civilizations, yet they left very different archaeological signatures. This variability in the past suggests that ancient civilizations might have taken forms we haven't yet imagined. Anthropologists have long recognized that civilization is better understood as a spectrum rather than a binary condition. Societies develop complexity gradually and unevenly, with some aspects advancing more rapidly than others. A society might develop sophisticated astronomical knowledge without developing writing, or create complex trade networks without building cities. The path from simple hunting and gathering to complex civilization is not linear, nor does it necessarily lead to the same endpoints. This spectrum perspective is crucial for our investigation because it opens up possibilities we might otherwise miss. An ancient civilization might not have resembled our modern industrial society at all. It might have been primarily agricultural, but with surprising technological sophistication. It might have been nomadic, but with complex social organization and advanced knowledge systems. It might have developed along entirely different trajectories than any civilization we know. The archaeological record provides tantalizing examples of complexity that doesn't fit neat categories. Çatalhöyük, a Neolithic settlement in Turkey dating to around 7,500 BCE, challenges our assumptions about early civilization. This site shows evidence of sophisticated art, complex social organization, and advanced building techniques, yet lacks many features we associate with civilization. There are no monumental buildings, no clear evidence of social hierarchy, no writing system. The inhabitants of Çatalhöyük created elaborate wall paintings depicting animals, humans, and mysterious symbols. They built their houses in a unique style, entering through the roof rather than ground-level doors. They practiced sophisticated burial rituals and showed evidence of long-distance trade networks. Yet archaeologists debate whether this constitutes a civilization or represents some other form of complex society. Similar ambiguities appear throughout the archaeological record. The builders of Stonehenge and other megalithic monuments clearly possessed sophisticated engineering knowledge and complex social organization, yet they left no cities and no writing. The mound-building cultures of North America created earthworks that rival any ancient monuments in their scale and precision, yet they developed along very different lines than old-world civilizations. These examples remind us that human societies have found many different ways to organize themselves and express complexity. If we're looking for traces of ancient civilizations, we cannot assume they would have resembled modern industrial society or even historical civilizations with which we're familiar. The role of symbols, art, and culture in defining civilization deserves special attention. Often, these are our first clues to cognitive sophistication and complex social organization. The cave paintings of Lascaux and Altamira demonstrate sophisticated artistic ability and possibly complex symbolic thinking tens of thousands of years ago. The Venus figurines found across Ice Age Europe suggest shared cultural concepts across vast distances and time periods. Art and symbols often outlast more practical artifacts because they're frequently created with permanent materials and sometimes preserved in favorable conditions. More importantly, they represent something uniquely important about intelligent beings: the capacity for abstract thought, cultural transmission, and meaning-making beyond immediate survival needs. But artistic expression can take forms that wouldn't necessarily preserve over geological time. Music, dance, oral traditions, body painting, and temporary installations might have been the primary artistic expressions of some ancient societies. These would leave no direct archaeological trace, reminding us again of the preservation bias that affects our understanding of the past. The development of technology represents another crucial aspect of civilization that might leave detectable traces. But here, too, we must think broadly about what constitutes technology. We tend to focus on tool-making and materials processing: stone tools, metallurgy, ceramics. But technology also includes knowledge systems, agricultural techniques, architectural methods, and organizational innovations. Some technologies are more likely to leave lasting traces than others. Metallurgy produces distinctive chemical signatures that can persist in sediments. Large-scale agriculture alters landscapes in ways that might remain detectable for extended periods. Quarrying and mining operations create distinctive geological features. But other technologies, organic chemistry, biological manipulation, energy systems based on renewable resources, might leave little direct evidence. The question of energy use is particularly important when we consider industrial civilizations. Our modern civilization is defined in large part by our massive consumption of fossil fuels, which produces distinctive chemical signatures in the environment. But an ancient industrial civilization might have developed along different energy pathways, perhaps relying more heavily on renewable sources, or developing entirely different approaches to energy generation and use. Social organization represents another dimension of civilization that might leave subtle but detectable traces. Large-scale societies require systems for moving goods, information, and people across distances. They typically involve some degree of specialization, which creates distinctive patterns of resource use and waste production. They often involve modifications to the landscape for agricultural, transportation, or defensive purposes. These organizational aspects of civilization might actually be more likely to leave long-term traces than individual artifacts. A city might crumble and disappear, but the agricultural terraces that supported it might remain visible in the landscape for much longer periods. Trade networks might outlast individual settlements, creating distinctive patterns in the distribution of materials and artifacts. Religious and ceremonial aspects of civilization also deserve consideration. Many early civilizations devoted enormous resources to religious architecture and practices. These investments often produce the most durable artifacts: temples built of stone, elaborate burial complexes, massive earthworks for ceremonial purposes. If ancient civilizations followed similar patterns, their religious and ceremonial sites might represent our best chance of finding preserved evidence. However, we must also consider the possibility that ancient civilizations might have developed very different relationships with permanence and monumentality. Perhaps they valued impermanence, creating elaborate but temporary structures. Perhaps they developed spiritual or philosophical systems that discouraged permanent construction. Perhaps they invested their surplus resources in activities that would leave no archaeological trace. The temporal dimension of civilization is equally important. Civilizations rise and fall on different timescales. Some emerge rapidly and collapse within centuries. Others develop gradually over millennia and persist for extended periods. Some cycle through phases of complexity and simplification. If we're looking for evidence of ancient civilizations, we need to consider not just their peak development, but their entire life cycle. The collapse of civilizations is particularly relevant to our investigation. Archaeological evidence shows that even sophisticated civilizations can disappear with surprising completeness. The Maya cities of the Classic period were largely abandoned and swallowed by jungle. The Indus Valley civilization vanished so thoroughly that it wasn't rediscovered until the 20th century. These examples remind us that civilizations can indeed disappear from the landscape, leaving only subtle traces for future investigators to discover. As we prepare to examine the specific scientific hypothesis about ancient industrial civilizations, this broad perspective on what constitutes civilization becomes crucial. We cannot assume that ancient civilizations would have resembled our own in their technology, organization, or environmental impact. We must be open to the possibility that intelligence and complexity might have taken forms we haven't yet imagined, while remaining rigorous about what traces such societies might realistically leave behind in the geological record. The Silurian hypothesis. In 2018, two respected scientists published a paper that would challenge fundamental assumptions about Earth's history and our place within it. Gavin Schmidt, director of NASA Goddard Institute for Space Studies and one of the world's leading climate modelers, joined forces with Adam Frank, an astrophysicist at the University of Rochester who studies the long-term evolution of civilizations. Together, they posed a question that bridged disciplines and timescales. If an industrial civilization had existed on Earth millions of years before humans, would we be able to detect it? Their paper, published in the journal Astrobiology, was titled The Silurian Hypothesis. Would it be possible to detect an industrial civilization in the geological record? The name was borrowed from a 1970 episode of Doctor Who featuring an ancient reptilian species called the Silurians who had supposedly ruled Earth before mammals. But Schmidt and Frank's investigation was grounded not in science fiction, but in rigorous analysis of geological processes, climate science, and the emerging field of astrobiology. The timing of their collaboration was not coincidental. As humanity grapples with climate change and begins to leave distinctive signatures in Earth's geological record, scientists are increasingly interested in what these signatures might tell future investigators about our civilization. This perspective naturally led to the reverse question: might previous civilizations have left similar signatures that we haven't yet recognized? Schmidt brought to the collaboration his deep expertise in Earth's climate system and the complex interactions between atmospheric composition, ocean circulation, and global temperature. His work on modern climate change had made him acutely aware of how human activities are altering the planet's fundamental systems in ways that will likely persist long after our current civilization ends. Frank contributed his broader perspective on the evolution of technological civilizations and the long-term survival challenges facing any intelligent species. Their hypothesis was not that ancient industrial civilizations definitely existed, but rather that the question deserved serious scientific investigation. They argued that if we're going to search for signs of intelligence elsewhere in the universe, we should first understand what signs of intelligence look like in our own planet's deep past. This approach could help us develop better methods for detecting technological civilizations and better understand the long-term sustainability challenges facing any advanced society. The paper's methodology was elegant in its simplicity. Schmidt and Frank asked, what traces would our current industrial civilization leave in the geological record, and how long would those traces remain detectable? Then they worked backward, asking what similar traces from ancient civilizations might look like and whether any had been detected in existing geological data. Their analysis focused on three main categories of evidence: geological markers, isotopic signatures, and chemical indicators. Each category offered different insights into the possible traces of ancient industrial activity, and each had different preservation potentials over millions of years. Geological markers represent the most direct, but also most fragile category of evidence. These would include physical structures, modified landscapes, and accumulated waste products. Schmidt and Frank noted that while individual buildings and artifacts would almost certainly not survive millions of years, large-scale landscape modifications might leave more persistent traces. Consider the scale of modern human impact on Earth's surface. We've moved more rock and sediment than all natural erosion processes combined. We've created artificial lakes, leveled mountains, and altered the courses of rivers. We've extracted billions of tons of materials from the ground and redistributed them across the planet's surface. Some of these modifications create distinctive geological features that might remain detectable for extended periods. Mining operations, in particular, create unique signatures in the geological record. The extraction of coal, oil, metal ores, and other resources leaves characteristic patterns in sedimentary layers. These extraction signatures might persist much longer than the civilizations that created them. Similarly, the waste products from industrial processes, slag heaps, tailings ponds, and contaminated soils create distinctive chemical and mineralogical signatures that could potentially be detected millions of years later. However, geological markers face significant preservation challenges. Erosion, sedimentation, and tectonic activity would gradually erase or bury most surface modifications. The timescales over which these processes operate mean that only the most massive and well-situated geological modifications would have any chance of remaining detectable after millions of years. Isotopic signatures offered Schmidt and Frank a more promising avenue for detection. Isotopes are variants of chemical elements that have different numbers of neutrons, but the same number of protons. The ratios of different isotopes in natural materials can serve as fingerprints for specific processes, including industrial activities. Modern industrial civilization has created distinctive isotopic signatures in several ways. The burning of fossil fuels has altered the ratio of carbon isotopes in the atmosphere, because fossil fuels are depleted in the heavier carbon-13 isotope relative to carbon-12. This signature has been incorporated into tree rings, ocean sediments, and other natural archives, creating a permanent record of industrial carbon emissions. Nuclear weapons testing and nuclear power have introduced artificial radioactive isotopes into the environment. Some of these isotopes, like plutonium-239, are extremely rare in nature and serve as unambiguous markers of technological activity. Others, like carbon-14 from nuclear weapons testing, have altered the natural isotopic composition of the atmosphere in ways that will remain detectable for thousands of years. The processing of metals and minerals also creates characteristic isotopic signatures. Lead from different sources has distinctive isotopic compositions, allowing archaeologists to trace ancient trade networks and identify the sources of metal artifacts. Similar isotopic fingerprinting might reveal the industrial processing of materials by ancient civilizations, even if no direct artifacts survived. Schmidt and Frank noted that isotopic signatures have several advantages over other types of evidence. They can be preserved in sedimentary layers and incorporated into the long-term geological record. They're extremely difficult to produce by natural processes alone, making them potentially reliable indicators of technological activity. And they can be detected using sophisticated analytical techniques that are becoming increasingly sensitive and precise. Chemical indicators represented the third major category of potential evidence. Modern industrial civilization has introduced thousands of synthetic chemicals into the environment, many of which are completely unknown in nature. These include pesticides, pharmaceuticals, industrial solvents, and synthetic polymers like plastics. Some of these synthetic chemicals are remarkably persistent in the environment. Chlorofluorocarbons, CFCs, once widely used as refrigerants and aerosol propellants, can persist in the atmosphere for decades to centuries. Certain pesticides and industrial chemicals can accumulate in sediments and remain stable for extended periods. Even plastics, despite their reputation for persistence, would likely break down completely over millions of years, but they might leave distinctive chemical signatures in the process. The authors were particularly interested in chemicals that might indicate energy production and consumption. The combustion of fossil fuels produces not just carbon dioxide, but a complex mixture of other compounds, including nitrogen oxides, sulfur compounds, and various organic molecules. These combustion products create distinctive chemical signatures in ice cores, lake sediments, and other environmental archives. More speculatively, Schmidt and Frank considered what chemical signatures might be left by alternative energy systems. Nuclear fission produces distinctive isotopic signatures and long-lived radioactive waste products. Fusion power, if ever developed, might leave different but equally distinctive traces. Even renewable energy systems might leave chemical signatures through the materials used in their construction and the industrial processes required to build them. The paper also addressed the temporal aspects of detection. Different types of signatures persist for different lengths of time. Isotopic signatures in long-lived minerals might remain detectable for millions or even billions of years. Chemical signatures in sediments might persist for thousands to millions of years, depending on the specific compounds and environmental conditions. Geological signatures might be the most variable, with some features being erased within thousands of years, while others might persist for much longer periods. Schmidt and Frank's analysis revealed both the possibilities and limitations of detecting ancient industrial civilizations. On one hand, Industrial activity does leave distinctive traces that can be preserved in the geological record. On the other hand, these traces fade over time and become increasingly difficult to distinguish from natural variations in Earth systems. Their work also highlighted the importance of understanding natural variability in Earth systems. The planet's climate, atmospheric composition, and geochemical cycles have fluctuated dramatically throughout Earth's history due to natural causes. Any signatures of ancient industrial activity would have to be distinguished from this natural background variability, which requires detailed knowledge of how Earth systems behave over long timescales. Perhaps most importantly, the Silurian hypothesis forced scientists to think more carefully about what constitutes evidence of intelligence and technology. The signatures that Schmidt and Frank identified are indirect. They indicate large-scale environmental modification rather than intelligence per se. This raises profound questions about how we might recognize intelligence that developed along different pathways than our own. The paper sparked intense discussion among geologists, climatologists, astrobiologists, and archaeologists. Some criticized it for being too speculative, arguing that there was no credible evidence for ancient industrial civilizations, and that the hypothesis was therefore not scientifically useful. Others embraced it as an important thought experiment that could improve our methods for detecting technological civilizations and our understanding of humanity's environmental impact. Schmidt and Frank themselves were careful to emphasize that their hypothesis was not a claim that ancient civilizations existed, but rather a framework for thinking about how such civilizations might be detected if they had existed. They noted that the absence of obvious evidence for ancient industrial civilizations might actually tell us something important about the rarity or short duration of such civilizations, or about the efficiency with which Earth erases evidence of past activity. The Silurian hypothesis also has implications for astrobiology and the search for extraterrestrial intelligence. If industrial civilizations can exist and disappear with relatively little trace, this might help explain why we haven't detected signs of intelligence elsewhere in the universe. It might also provide guidance for what kinds of signatures to look for when examining other planets for signs of past or present technological activity. As we'll see in subsequent parts of this investigation, the Silurian hypothesis has opened up new avenues of research and forced scientists to reconsider evidence from Earth's deep past with fresh eyes. It represents a perfect example of how asking the right question can illuminate new possibilities and challenge our assumptions about the world around us. The hypothesis stands as a testament to the power of rigorous scientific imagination, the ability to envision possibilities that stretch our understanding while remaining firmly grounded in empirical evidence and natural law. Whether or not ancient industrial civilizations actually existed on Earth, the Silurian hypothesis has already proven valuable in helping us think more clearly about intelligence, technology, and the long-term relationship between civilizations and their planetary environments. As our investigation continues, we'll examine what the geological record actually shows, explore the specific signatures that modern civilization is leaving behind, and consider what these findings might tell us about the deep past and the far future. The question of whether we were the first remains open, but the framework for answering it has never been clearer. The implications of Schmidt and Frank's work extend far beyond academic curiosity. Their methodology provides a mirror for examining our own civilization's impact on Earth systems. Every chemical signature, every isotopic anomaly, every geological modification we create today will become part of the permanent record that future investigators, whether human or otherwise, might use to understand our time on this planet. Consider the irony inherent in this investigation. We are simultaneously the civilization leaving traces and the civilization searching for them. Our industrial activities are creating the very signatures that we're learning to recognize as indicators of technological civilization. This dual perspective offers unique insights into both the detectability and the meaning of such signatures. The carbon isotope anomaly created by fossil fuel combustion serves as perhaps the clearest example of how industrial activity becomes embedded in the geological record. When we burn coal, oil, and natural gas, we're releasing carbon that was locked away in rocks for millions of years. This ancient carbon has a distinctive isotopic signature. It's depleted in carbon-13 relative to carbon from living organisms, or the atmosphere. This depletion signature is now being incorporated into every carbon-bearing material formed on Earth's surface. Tree rings from around the world show the progressive decline in carbon-13 ratios since the beginning of the Industrial Revolution. Ocean corals are recording the same signature in their calcium carbonate skeletons. Even the shells of tiny marine organisms floating in the ocean are incorporating this isotopic fingerprint of human activity. The preservation potential of this signature is remarkable. Once incorporated into limestone, coal deposits, or organic-rich sediments, these isotopic ratios could potentially remain detectable for millions of years. Future geologists examining rock layers from our era would find a distinctive carbon isotope anomaly that would be difficult to explain through natural processes alone. But the carbon signature is just the beginning. The large-scale extraction and processing of metals has created unprecedented concentrations of certain elements in specific locations. Lead concentrations in Greenland ice cores show spikes corresponding to Roman silver mining and smelting operations 2,000 years ago. The lead signatures from our modern industrial activities dwarf even these historical peaks. Similarly, the mining and processing of rare earth elements for modern electronics has created distinctive geochemical signatures in mining regions around the world. These elements are naturally rare and typically dispersed throughout Earth's crust. Concentrating them into industrial products and subsequently into waste streams creates anomalous geochemical patterns that would be difficult to explain without invoking technological processes. The nuclear age has added an entirely new dimension to humanity's geological signature. Natural uranium ore contains specific ratios of uranium isotopes that reflect billions of years of radioactive decay. Nuclear reactors alter these ratios in characteristic ways, creating artificial isotopic compositions that simply don't occur in nature. The spent fuel from nuclear power plants contains a complex mixture of artificial isotopes, many of which have half-lives extending into the hundreds of thousands of years. Nuclear weapons testing has distributed these artificial isotopes globally. Plutonium-239, an isotope that is vanishingly rare in nature, can now be detected in sediments around the world as a direct consequence of atmospheric nuclear testing in the 1950 and 1960. This global plutonium signature represents an unambiguous marker of technological civilization that will remain detectable for millions of years. The scale of human impact on nitrogen cycling also creates distinctive signatures that could persist in the geological record. The industrial production of ammonia for fertilizers has doubled the amount of biologically available nitrogen in Earth's ecosystems. This excess nitrogen creates characteristic isotopic signatures in soils and sediments, and has fundamentally altered the nitrogen content of many natural systems. These nitrogen signatures are particularly significant because they represent a global-scale modification of a fundamental biogeochemical cycle. Natural variations in nitrogen isotope ratios are typically small and gradual. The rapid, large-scale changes associated with industrial nitrogen fixation create anomalies that would be difficult to explain through natural processes, especially when combined with other indicators of technological activity. Schmidt and Frank's analysis also revealed the importance of considering the duration and intensity of industrial activity. A brief period of intense industrial activity might leave different signatures than a longer period of moderate activity. The signatures we're creating today reflect roughly 2 centuries of increasingly intensive industrial activity, but this represents an extremely brief moment in geological time. The question of whether these signatures would be recognizable millions of years from now depends partly on how long our industrial civilization persists and how it evolves. If we continue burning fossil fuels at current rates for several more centuries, the carbon isotope signal will become even more pronounced. If we transition to renewable energy sources, the signal might level off, but would still represent a distinctive anomaly in the geological record. The development of new technologies also creates new opportunities for detection. Advanced analytical techniques allow scientists to detect smaller and smaller concentrations of trace elements and to resolve isotopic ratios with increasing precision. Techniques that didn't exist when Schmidt and Frank wrote their paper might reveal subtle signatures of ancient technological activity that were previously undetectable. Mass spectrometry instruments can now measure isotopic ratios with precision, better than 1 part in a million. This sensitivity makes it possible to detect extremely subtle anomalies that might indicate past technological activity. Similarly, advances in geochemical analysis allow scientists to identify trace concentrations of synthetic compounds and artificial isotopes in environmental samples. The temporal resolution of these analyses is also improving. Scientists can now extract detailed geochemical records from sediment cores, ice cores, and other natural archives that provide year-by-year or even season-by-season records of past environmental conditions. This high-resolution perspective makes it possible to identify rapid changes or anomalous periods that might indicate technological activity. However, the improving sensitivity of analytical techniques also reveals the complexity of natural geochemical processes. As scientists learn more about how Earth systems operate over long timescales, they discover natural processes that can create signatures previously thought to be indicative of technological activity. This ongoing refinement of our understanding emphasizes the importance of rigorous analysis and multiple lines of evidence. The search for ancient industrial civilizations also highlights the importance of understanding Earth's natural variability. The planet has experienced dramatic climate changes, massive volcanic eruptions, asteroid impacts, and other catastrophic events throughout its history. These natural events can create geochemical signatures that might be mistaken for evidence of technological activity. For example, large volcanic eruptions can inject massive amounts of sulfur compounds into the atmosphere, creating acid rain that can alter the chemistry of soils and sediments over wide areas. Asteroid impacts can create shocked minerals and distinctive geochemical signatures that persist for millions of years. Even natural climate changes can alter the isotopic composition of atmospheric gases and create anomalies in the geological record. Distinguishing between natural and technological signatures requires careful analysis of multiple indicators and a deep understanding of how natural systems operate. This challenge emphasizes the interdisciplinary nature of the investigation. It requires expertise in geology, geochemistry, climatology, archaeology, and even astrobiology to properly evaluate potential evidence. The Silurian hypothesis also raises profound questions about the nature and sustainability of technological civilizations. If ancient industrial civilizations did exist and subsequently disappeared, what might have caused their collapse? Did they exhaust their resources? Did they trigger environmental changes that made their planet uninhabitable? Did they transition to forms of technology that leave different signatures? These questions have obvious relevance to our own civilization's future prospects. The signatures we're leaving in the geological record reflect not just our technological capabilities, but also our environmental impacts. The same industrial processes that create distinctive geological signatures are also driving climate change, biodiversity loss, and other environmental challenges that threaten our long-term survival. Understanding how technological civilizations interact with their planetary environments represents a crucial challenge for astrobiology and the search for extraterrestrial intelligence. If technological civilizations typically have brief lifespans due to environmental or resource constraints, this might help explain why we haven't detected signs of intelligence elsewhere in the universe. Alternatively, if civilizations can successfully navigate these challenges and persist for millions of years, they might develop technologies and social systems that leave very different signatures than those produced by early industrial phases. A mature technological civilization might rely primarily on renewable energy sources, practice extensive recycling and resource conservation, and maintain a much smaller environmental footprint than civilizations in their industrial growth phase. The possibility of such technological maturation adds another layer of complexity to the search for ancient civilizations. We're learning to recognize the signatures of industrial civilizations like our own, but we might completely miss the signatures of civilizations that have evolved beyond the resource-intensive industrial phase. Their traces might be so subtle or so different from our expectations that we wouldn't recognize them as indicators of intelligence. This perspective suggests that the Silurian hypothesis is not just about detecting ancient civilizations, but about understanding the possible trajectories of technological development. By studying the signatures that different types of technological activity might leave behind, we can better understand the range of possibilities for how civilizations might develop and persist over long timescales. The hypothesis also provides a framework for thinking about our own civilization's legacy. What signatures will we leave behind? How will future investigators understand our time on Earth? What can we do to ensure that our impact on the planet reflects our values and aspirations rather than merely our resource consumption and waste production? These questions bring the investigation full circle, from the deep past to the far future, from speculation about ancient civilizations to practical concerns about our own survival and legacy. The Silurian hypothesis ultimately forces us to think carefully about what it means to be a technological civilization on a finite planet, and what responsibilities that entails for both our predecessors and our successors in the vast sweep of cosmic time. The methodology developed by Schmidt and Frank has already begun to influence research in unexpected ways. Geologists examining ancient climate records are now more alert to the possibility that some anomalies in the data might reflect technological rather than natural causes. This heightened awareness has led to more careful analysis of unusual geochemical signatures, and has improved our understanding of both natural and potentially artificial processes. One particularly intriguing aspect of this research involves the study of the Paleocene-Eocene thermal maximum, a period of rapid global warming that occurred about 56 million years ago. During this event, massive amounts of carbon were released into the atmosphere, causing global temperatures to rise by 5 to 8 degrees Celsius. The carbon isotope signatures from this period show characteristics similar to those we might expect from massive fossil fuel combustion, raising the tantalizing question of whether this event might have had a technological component. However, most scientists remain convinced that the Paleocene-Eocene thermal maximum resulted from natural processes, possibly involving the rapid release of methane from ocean sediments or massive volcanic activity. The scale and duration of the event, lasting roughly 200,000 years, would require a technological civilization of unprecedented longevity and scale. Nevertheless, the comparison highlights how difficult it can be to distinguish between natural and technological causes for ancient environmental changes. The search for ancient technological signatures has also led scientists to examine more carefully the traces left by known civilizations. Archaeological investigations of Roman and medieval mining operations have revealed that even pre-industrial civilizations could leave distinctive geochemical signatures. Lead pollution from Roman silver mining can be detected in Greenland ice cores, demonstrating that technological activities can create global-scale environmental signatures even without modern industrial techniques. These historical examples provide valuable calibration points for understanding how technological signatures scale with the intensity and duration of industrial activity. They also demonstrate that the transition from natural to technological environmental influences began much earlier than the Industrial Revolution, albeit at much smaller scales. The development of new analytical techniques continues to expand our ability to detect subtle environmental changes. Advances in laser ablation, mass spectrometry allow scientists to analyze microscopic samples with extraordinary precision, potentially revealing technological signatures in individual mineral grains or fossil specimens. New isotope systems are being explored as potential indicators of technological activity, including isotopes of sulfur, oxygen, and various trace metals. These technological advances raise the intriguing possibility that we might eventually detect signatures of ancient civilizations that are currently below our detection threshold. As analytical sensitivity improves and our understanding of geochemical processes deepens, we might discover anomalies in the geological record that we currently dismiss as natural variation or analytical noise. The psychological and philosophical implications of the Silurian hypothesis deserve careful consideration. The possibility that we were not the first technological civilization challenges deeply held beliefs about human uniqueness and our special place in Earth's history. This challenge parallels other scientific revolutions that displaced humanity from the center of the universe, from the Copernican realization that Earth is not the center of the solar system, to Darwin's demonstration that humans evolved from earlier life forms. Yet the hypothesis also offers a form of cosmic companionship. If other civilizations did exist in Earth's deep past, we are not alone in having developed intelligence and technology. We are part of a longer story of intelligence on our planet, participants in an ancient tradition of beings who learn to shape their environment and contemplate their place in the cosmos. This perspective might also provide valuable insights into the challenges facing technological civilizations. If ancient civilizations did exist and subsequently disappeared, their fate might offer lessons about the long-term sustainability of technological development. Did they collapse due to environmental overreach? Did they exhaust critical resources? Did they transition to forms of existence that leave no geological trace? Or did they simply evolve beyond the need for large-scale environmental manipulation? The absence of obvious evidence for ancient civilizations might itself be significant. If technological civilizations were common in Earth's past, we might expect to find multiple layers containing their signatures in the geological record. The apparent absence of such layers might indicate that technological civilizations are rare, that they have brief lifespans, or that they quickly evolve beyond the resource-intensive phases that leave strong geological signatures. This last possibility is particularly intriguing. Our current understanding of technological development is based on a single example, our own civilization, which has followed a particular trajectory from agriculture through industrialization toward increasingly sophisticated information technologies. But this trajectory is not necessarily inevitable or universal. Other civilizations might have developed along entirely different pathways, emphasizing biological rather than mechanical technologies, or developing sophisticated knowledge systems without large-scale environmental manipulation. The concept of technological sustainability offers another lens through which to examine the Silurian hypothesis. A truly sustainable technological civilization would minimize its environmental impact while maximizing its capability to persist over long timescales. Such a civilization might leave very subtle geological signatures, making it difficult to detect using current methods. This raises profound questions about the relationship between detectability and sustainability. The signatures that we're learning to recognize as indicators of technological civilization, carbon isotope anomalies, trace metal pollution, artificial isotopes, are largely the byproducts of unsustainable practices. A civilization that successfully solved its sustainability challenges might become essentially invisible from a geological perspective. The implications extend to astrobiology and the search for extraterrestrial intelligence. If technological civilizations typically evolve toward minimal environmental impact, this might help explain why we haven't detected obvious signs of technology elsewhere in the universe. Advanced civilizations might be present but undetectable using current methods that focus on high-energy signatures and large-scale environmental modifications. The Silurian hypothesis also highlights the importance of preserving Earth's geological record. Every sediment core, every ice core, every carefully preserved stratigraphic sequence represents an irreplaceable archive of Earth's history. As human activities increasingly modify the planet's surface, we risk losing access to these archives before we fully understand what they might tell us. Climate change, in particular, threatens many of the natural archives that preserve long-term environmental records. Melting ice caps are eliminating ice core records that took millennia to accumulate. Rising sea levels and changing precipitation patterns are altering the conditions that preserve sedimentary records. Ocean acidification is dissolving the carbonate shells that provide crucial information about past ocean conditions. The urgency of preserving these records has led to increased efforts to collect and analyze geological archives from around the world. International collaborations are working to extract and preserve ice cores, sediment cores, and other environmental records before they are lost to ongoing environmental changes. These efforts represent a race against time to preserve Earth's memory of its own history. The technological tools available for this work continue to improve rapidly. Portable analytical instruments allow scientists to conduct sophisticated geochemical analyses in the field. Improved drilling techniques make it possible to extract longer and more complete sediment records. Advanced statistical methods help scientists identify subtle patterns and anomalies in large datasets. These improvements in capability come at a crucial time. The window for collecting certain types of environmental records is closing rapidly due to ongoing climate change. At the same time, Our analytical capabilities are reaching the point where we might be able to detect extremely subtle signatures of ancient technological activity that were previously undetectable. The convergence of improving analytical capabilities with the urgent need to preserve environmental records creates unprecedented opportunities for investigating Earth's deep past. We may be living at a unique moment in history when we have both the technological capability and the preserved archives necessary to seriously investigate questions about ancient civilizations. The educational implications of the Silurian hypothesis are equally significant. The investigation forces students and researchers to think across multiple disciplines and timescales, developing the kind of systems thinking that is essential for addressing complex global challenges. It demonstrates how scientific questions can emerge from the intersection of different fields, and how collaborative research can address problems that no single discipline could tackle alone. The hypothesis also provides a powerful framework for thinking about environmental stewardship and sustainability. By examining our own civilization's geological signature, we gain perspective on the scale and permanence of human environmental impacts. This perspective can inform policy decisions and individual choices about resource use, waste generation, and environmental protection. As we continue to investigate the possibility of ancient civilizations, we are simultaneously learning about our own civilization's impact and future prospects. The traces we are leaving in the geological record will be our legacy to future investigators, whether they are our descendants or entirely different forms of intelligence that might evolve on Earth in the distant future. The Silurian hypothesis reminds us that we are both the investigators and the investigated, both the seekers and the sought, in the grand story of intelligence on our ancient and ever-changing planet. The fragility of our legacy. Imagine waking up tomorrow to find that every human being on Earth has simply vanished. The cities stand empty, power grids begin to fail, and nature starts its relentless work of reclamation. This thought experiment, while unsettling, provides crucial insight into what traces our civilization might leave for future investigators to discover millions of years from now. The immediate aftermath would be dramatic but deceptively temporary. Within hours, subway systems would begin flooding without pumps to keep them dry. Traffic lights would fail, planes would fall from the sky, and nuclear reactors would begin emergency shutdowns. But these immediate catastrophes, dramatic as they seem, would represent only the first moments in a much longer story of dissolution and decay. After 1 year, the changes would already be striking. Wooden structures would begin to rot and weaken. Paint would start to peel and fade under ultraviolet radiation. Vegetation would begin to sprout through cracks in pavement, and rooftop gardens would go wild. Animals would start to reclaim urban spaces, with domestic animals either adapting to feral life or perishing without human care. But the basic structure of our cities would still be recognizably human. The power grid failures would cascade through our technological systems. Without electricity, refrigeration systems would fail, allowing food to spoil and bacteria to flourish. Computer servers would shut down, taking with them vast quantities of digital information. The Internet, that repository of human knowledge and communication, would effectively cease to exist within months of the last human disappearance. Yet even in this first year, some of our most durable creations would show remarkable persistence. The concrete cores of skyscrapers would remain structurally sound. Major highways and bridges would continue to carry the phantom traffic of wind and debris. Underground infrastructure, subway tunnels, utility corridors, basements would provide protection from surface weathering processes. After 100 years, the transformation would be profound. Most wooden buildings would have collapsed or been consumed by fire, insects, and decay. Steel structures would show significant corrosion, particularly in humid coastal environments where salt spray accelerates oxidation. Glass windows would begin to fail, not from dramatic shattering but from the gradual expansion and contraction that creates stress fractures over decades. Plant life would have made dramatic inroads into urban environments. Tree roots would exploit every crack in pavement, gradually breaking apart roads and sidewalks. Ivy and other climbing plants would cover building facades, trapping moisture and accelerating decay processes. In some climates, entire city blocks might disappear beneath rapidly growing forests. The absence of human maintenance would become increasingly evident. Without regular cleaning and repair, building facades would stain and crumble. Roofing materials would fail, allowing water to penetrate structures and accelerate internal decay. Metal infrastructure would rust and weaken, leading to progressive structural failures. Yet certain materials would demonstrate remarkable durability. Concrete, despite its reputation for relatively short lifespans in human terms, could persist for centuries when protected from freeze-thaw cycles and chemical attack. Some of our largest structures, dams, highway overpasses, building foundations would remain recognizable even after a century of neglect. After 10,000 years, the pace of change would depend heavily on climate and geological conditions. In stable, arid environments, some structures might remain surprisingly intact. The pyramids of Egypt and stone monuments around the world demonstrate that massive stone construction can persist for millennia with minimal maintenance. However, in most environments, 10 millennia would be sufficient to erase most surface traces of our civilization. The great cities would be reduced to subtle mounds in the landscape, detectable mainly through soil chemistry and the occasional fragment of durable material. Concrete would have cracked and spalled under countless freeze-thaw cycles. Steel would have oxidized to unrecognizable rust stains in the soil. The most persistent traces would be underground. Subway systems, particularly those carved through solid rock, might preserve their basic structure for tens of thousands of years. Deep basements and tunnels could serve as time capsules, protecting artifacts from surface weathering processes. Mining shafts and deep foundations would create distinctive signatures in the geological record. Archaeological materials would face variable preservation challenges. Metals would oxidize, but their corrosion products might create distinctive geochemical signatures in surrounding soils. Ceramics and glass would be more durable than organic materials, but would gradually weather and fragment. Plastics would break down through photodegradation and bacterial action, but their chemical components might persist in altered forms. The transformation after 1 million years would be nearly complete. Surface traces of our civilization would be virtually eliminated through erosion, sedimentation, and tectonic activity. Mountain ranges rise and fall over such timescales. River valleys migrate across landscapes. Coastlines advance and retreat with changing sea levels. Yet even after 1 million years, subtle traces might persist for those who knew how to look for them. Deep mines would create distinctive geological features that could remain recognizable. The distribution of metals and rare earth elements would show patterns that reflect our industrial activities. Isotopic signatures in sedimentary rocks would preserve evidence of our massive fossil fuel combustion and nuclear activities. The most enduring chemical traces would be those incorporated into stable mineral phases or long-lived sedimentary sequences. Carbon isotope ratios altered by fossil fuel combustion could persist in limestone formations and organic-rich sediments. Lead isotope signatures from industrial activities would remain detectable in lake sediments and ice sheets, assuming they survived other geological processes. Artificial isotopes from nuclear activities would present perhaps the most unambiguous evidence of technological civilization. Plutonium-239, virtually absent in nature, would remain detectable for hundreds of thousands of years. Other artificial isotopes, while shorter-lived, would leave distinctive signatures in the geological record that would be difficult to explain through natural processes alone. The global distribution of synthetic chemicals would also leave subtle but persistent traces. While individual plastic molecules would break down, their degradation products might create distinctive chemical signatures in sedimentary layers. The massive redistribution of nitrogen through industrial fertilizer production would alter the nitrogen isotope ratios in soils and sediments worldwide. Perhaps most significantly, the sheer scale of human earth-moving activities would leave geological signatures that could persist for millions of years. We have moved more rock and sediment than all natural erosion processes combined, creating artificial topographic features and altering natural drainage patterns. These large-scale modifications to Earth's surface might remain detectable even after the structures that created them have completely disappeared. Mining activities, in particular, would leave distinctive geological signatures. Open-pit mines create artificial valleys that could remain recognizable for millions of years. Underground mines create void spaces and altered rock compositions that would be detectable through geophysical surveys. The redistribution of ore materials through industrial processes would create geochemical anomalies far from their natural sources. The preservation potential of different types of evidence varies dramatically with environmental conditions. Materials buried in dry, stable environments might persist far longer than those exposed to weathering and biological activity. Artifacts sealed in caves or deep underground could potentially survive for millions of years, while surface materials would be destroyed much more rapidly. Ironically, some of our most impressive achievements would leave the least permanent traces. The International Space Station, representing the pinnacle of human technological achievement, would eventually decay from orbit and burn up in the atmosphere, leaving no trace of its existence. Our digital archives, containing the accumulated knowledge and communication of billions of people, would vanish within decades without human maintenance of the storage systems. In contrast, some of our most environmentally damaging activities might leave the most persistent evidence. The chemical pollution from industrial activities, the artificial isotopes from nuclear testing, the altered atmospheric composition from fossil fuel combustion, these unintended consequences of our technological development might outlast all the monuments we've built to celebrate our achievements. This thought experiment reveals the profound challenge facing any attempt to detect ancient technological civilizations. The traces that would survive millions of years are not the traces we would expect based on our daily experience of civilization. Cities, roads, buildings, machines, all the obvious manifestations of our technological prowess would disappear relatively quickly on geological timescales. Instead, the most enduring evidence would be subtle, chemical, and easily overlooked. Future investigators would need to look not for ruins and artifacts, but for anomalous isotope ratios, unusual chemical compositions, and distinctive patterns in the distribution of elements. They would need to distinguish these artificial signatures from the countless natural processes that can create similar geochemical patterns. The fragility of our physical legacy stands in stark contrast to the magnitude of our environmental impact. While our buildings and machines will crumble to dust, the carbon dioxide we've added to the atmosphere will influence Earth's climate for hundreds of thousands of years. The species we've driven to extinction will remain extinct forever. The artificial isotopes we've created will decay according to the immutable laws of physics, serving as cosmic clocks marking the time of our existence. Understanding the fragility of our own legacy provides crucial context for evaluating the Silurian hypothesis. If our own advanced technological civilization would leave such subtle traces, we must be prepared for the possibility that evidence of ancient civilizations might be equally subtle and easily overlooked. The absence of obvious archaeological evidence doesn't necessarily mean that ancient technological civilizations never existed. It might simply reflect the efficiency with which geological time erases the obvious traces of intelligence. The language of the earth. Deep time the earth speaks, but in a language written in stone, ice, and sediment that requires patient translation by those who have learned to read its subtle grammar. Geologists have spent centuries developing the skills to interpret this vast archive, learning to extract stories of ancient climates, vanished oceans, and life forms that existed millions of years before humans walked the planet. Now, as we search for possible traces of ancient technological civilizations, we must push these interpretive skills to their limits, learning to recognize signatures so subtle they might easily be dismissed as natural variation. The fundamental principle underlying geological interpretation is uniformitarianism, the idea that the processes operating on Earth today are the same processes that operated in the past. By understanding how sediments form, how rocks weather, how isotopes fractionate, and how chemical elements move through Earth systems, geologists can work backward from present observations to reconstruct past conditions. But this reconstruction is never straightforward. The geological record is like a vast library where most of the books have been lost, and those that remain have pages missing, text smudged, and chapters rewritten by later events. Every rock formation, every sedimentary layer, every ice core represents a complex interplay of original deposition, subsequent alteration, and preservation processes that must be carefully disentangled. Sedimentary rocks provide the most detailed records of Earth's surface conditions through time. As particles settle from the water column in lakes and oceans, they create layers that chronicle changing environmental conditions. The size, composition, and chemistry of these particles reflect the climate conditions, biological productivity, and geological processes operating at the time of deposition. Reading these sedimentary archives requires understanding how different materials accumulate and preserve. Clay particles, weathered from continental rocks, carry information about rainfall patterns and chemical weathering rates. Carbonate minerals precipitated from seawater reflect ocean temperature and chemistry. Organic matter, when preserved under oxygen-poor conditions, provides records of biological productivity and atmospheric composition. The layering itself tells a story. Thin, regular layers might indicate seasonal cycles of deposition. Thick, chaotic layers might record catastrophic events like floods or volcanic eruptions. The presence or absence of certain types of layers can reveal major environmental changes, such as the transition from ice age to interglacial conditions, or the onset of major droughts. Ice cores from polar regions and high mountains provide some of the most detailed records of past atmospheric conditions. Each annual layer in an ice sheet preserves a sample of ancient atmosphere, including gases, dust, and chemical compounds that were present when the ice formed. By analyzing these trapped materials, scientists can reconstruct ancient temperatures, precipitation patterns, atmospheric composition, and even the timing and intensity of major volcanic eruptions. The resolution of ice core records is extraordinary. Individual annual layers can be counted and analyzed, providing records that extend back hundreds of thousands of years with year-by-year resolution. The chemical composition of the ice reflects the temperature at which it formed. Trapped air bubbles contain samples of ancient atmosphere, allowing scientists to measure past concentrations of carbon dioxide, methane, and other greenhouse gases. But ice cores also preserve evidence of human activities. Lead concentrations in Greenland ice cores show spikes corresponding to ancient metallurgy, including Roman silver mining operations, and the onset of leaded gasoline use in the 20th century. Sulfur compounds reflect both natural volcanic activity and industrial emissions. Even trace concentrations of artificial isotopes from nuclear testing can be detected in ice core records. Tree rings provide another high-resolution archive of environmental conditions, though their preservation potential over geological time is limited. Each ring reflects the growing conditions experienced by the tree during a particular year. Ring width indicates temperature and moisture conditions. Chemical composition reflects atmospheric chemistry and soil conditions. Isotope ratios in the wood cellulose provide detailed records of past climate conditions. The chemical analysis of geological samples has become extraordinarily sophisticated. Mass spectrometry instruments can measure isotope ratios with precision, better than 1 part in a million. X-ray fluorescence spectrometers can detect trace element concentrations at the parts per billion level. Electron microscopy can reveal the detailed structure and composition of individual mineral grains. This analytical precision allows scientists to detect extremely subtle signatures that might indicate past technological activity. Carbon isotope ratios can reveal the burning of fossil fuels. Lead isotope ratios can identify the smelting of metal ores. Concentrations of rare earth elements can indicate the processing of electronic materials. The challenge lies not in detecting these signatures, but in distinguishing them from natural processes that can create similar patterns. Natural processes can create geochemical anomalies that might be mistaken for evidence of technological activity. Large volcanic eruptions can inject massive amounts of sulfur and trace metals into the atmosphere, creating global-scale chemical signatures. Asteroid impacts can redistribute elements and create shocked minerals with unusual compositions. Even biological processes can concentrate certain elements and create distinctive geochemical patterns. The key to distinguishing natural from artificial processes lies in understanding the characteristic signatures of each. Natural processes typically operate over specific temporal and spatial scales and create patterns that reflect underlying physical and chemical laws. Technological processes, by contrast, can create patterns that violate these natural expectations, concentrating rare elements in unusual locations, creating isotope ratios that don't occur in nature, or producing chemical compounds that require high-temperature industrial processes. The temporal aspect is particularly important. Natural geochemical anomalies typically develop gradually over thousands to millions of years, reflecting the slow operation of geological processes. Technological signatures, by contrast, can appear rapidly in the geological record, reflecting the rapid development and deployment of industrial technologies. The global scale of modern technological signatures is also distinctive. While natural processes can create global-scale changes, they typically require extraordinary events like supervolcanic eruptions or asteroid impacts. The mundane operation of industrial civilization has created chemical signatures that can be detected worldwide, from urban centers to remote polar regions. Isotope geochemistry has emerged as one of the most powerful tools for detecting potential technological signatures. Different isotopes of the same element behave almost identically in most chemical and biological processes, but they can be separated by certain industrial processes or created through nuclear reactions. This makes isotope ratios extremely sensitive indicators of technological activity. The carbon isotope system provides a clear example of how technological activity creates distinctive signatures. Fossil fuels are depleted in the heavy carbon-13 isotope relative to carbon-12, reflecting the biological processes that originally formed the organic matter. When we burn fossil fuels, we're releasing carbon with a distinctive isotopic signature that becomes incorporated into all carbon-bearing materials formed at Earth's surface. This fossil fuel signature is now detectable in tree rings, coral skeletons, lake sediments, and atmospheric carbon dioxide around the world. The signature began appearing in the geological record during the Industrial Revolution and has become progressively stronger as fossil fuel use has increased. This global carbon isotope anomaly represents clear evidence that a technological civilization has been altering Earth's atmospheric chemistry. Similar technological signatures exist for other isotope systems. Lead isotope ratios reflect the sources of lead ore and can reveal the smelting and use of lead-bearing materials. Sulfur isotope ratios can indicate the burning of fossil fuels or the processing of sulfur-bearing ores. Even nitrogen isotope ratios can reveal the large-scale production of artificial fertilizers. The nuclear age has created entirely new categories of isotopic signatures. Nuclear reactors alter the ratios of uranium isotopes in characteristic ways. Nuclear weapons testing has created artificial isotopes that simply don't exist in nature. These signatures provide unambiguous evidence of technological activity and will remain detectable in the geological record for hundreds of thousands to millions of years. The challenge of reading these isotopic signatures lies in understanding the natural background variability. Earth's isotope systems are not static. They vary naturally due to a wide range of geological, climatological, and biological processes. Volcanic activity can alter local and regional isotope ratios. Climate changes can affect biological fractionation processes. Even the evolution of life has altered Earth's isotope systems over geological time. Distinguishing technological signatures from this natural variability requires careful statistical analysis and multiple lines of evidence. A single anomalous isotope ratio might be explained by natural processes, but multiple independent isotope systems showing coordinated anomalies would be much more difficult to explain without invoking technological processes. The spatial distribution of geochemical anomalies also provides important clues about their origin. Natural processes typically create patterns that reflect underlying geological structures or environmental gradients. Technological processes, by contrast, might create patterns that reflect transportation networks, population centers, or industrial activities. The preservation of geochemical signatures over geological time depends on the specific elements and compounds involved and the environmental conditions at the site of deposition. Some signatures are remarkably stable and can persist for millions of years. Others are more ephemeral and might be destroyed by weathering, diagenesis, or metamorphism within thousands of years. Understanding these preservation processes is crucial for interpreting potential evidence of ancient technological civilizations. The signatures we can detect today from our own civilization represent only a subset of the total impact we're having on Earth systems. Many of our technological signatures will be destroyed by natural processes long before they could be detected by future investigators. Conversely, some signatures that seem minor today might become the primary evidence of our civilization for future investigators. The trace concentrations of artificial isotopes in deep ocean sediments might outlast all other evidence of human activity. The subtle alterations to atmospheric chemistry recorded in ice cores might provide the clearest signature of our industrial age. The development of new analytical techniques continues to expand our ability to read Earth's chemical archives. Advances in mass spectrometry allow measurement of increasingly subtle isotopic variations. New methods for analyzing organic compounds can detect trace concentrations of synthetic chemicals. Improved statistical techniques can identify patterns in complex datasets that might otherwise be dismissed as noise. These advancing capabilities raise the intriguing possibility that we might eventually detect signatures of ancient technological civilizations that are currently below our detection threshold. As we become better at reading Earth's chemical language, we might discover that some anomalies we currently attribute to natural processes actually reflect technological activity from the deep past. The language of deep time is written in elements and isotopes, in the slow accumulation of sediments, and the patient preservation of atmospheric samples in ancient ice. Learning to read this language has taken generations of dedicated scientific work, and we are still far from fluent. But as we develop our skills in geological translation, we open new possibilities for understanding Earth's history and our place within the vast story of intelligence on our planet. Evidence and anomalies throughout human history, people have discovered objects that seem to challenge our understanding of the past. Metallic spheres in ancient rock formations, delicate mechanisms in Roman shipwrecks, perfectly preserved artifacts in coal seems millions of years old. These discoveries, known as out-of-place artifacts or OOP arts, have sparked debates about ancient civilizations, time travel, and lost technologies. While most have conventional explanations, some continue to puzzle researchers and remind us how much we still don't know about Earth's deep history. The phenomenon of out-of-place artifacts reflects a fundamental challenge in interpreting the geological record. When we find something unexpected, our first assumption is often that it doesn't belong where we found it. A modern coin in an ancient stratum must have fallen through a crack. A sophisticated mechanism in a Roman wreck must be a later contamination. An artificial-looking object in million-year-old rock must be a natural formation that resembles human manufacture. This skepticism is scientifically justified. The overwhelming majority of claimed OOP arts do, indeed, have conventional explanations. Stratigraphic relationships can be deceptive, particularly in areas affected by erosion, burrowing animals, or human disturbance. Dating methods can be misapplied or misinterpreted. Natural processes can create objects that closely resemble artificial manufacture. Yet this same skepticism, while necessary for maintaining scientific rigor, might also blind us to genuine anomalies that could indicate unknown aspects of Earth's history. The challenge lies in applying appropriate analytical methods to distinguish between natural and artificial origins, while remaining open to the possibility that our current understanding of the past might be incomplete. One of the most famous categories of OOP arts involves metallic spheres found in Precambrian rock formations in South Africa. These spheres, found in pyrophyllite deposits estimated to be 2.8 billion years old, are nearly perfectly round and show parallel grooves around their equators. Their discoverers claimed they represented evidence of artificial manufacture by unknown beings in the distant past. Detailed analysis of these spheres reveals a more prosaic but equally fascinating origin. They are concretion's natural formations created when minerals precipitate from groundwater solutions. The spherical shape results from the uniform precipitation of minerals around nucleation points. The parallel grooves reflect the internal structure of the host rock and the flow patterns of the mineralizing fluids. Similar concretions form in many different geological environments and can create remarkably regular shapes that closely resemble artificial objects. The Moqui marbles of Utah, the Cannonball concretions of North Dakota, and the septarian nodules found worldwide all demonstrate nature's ability to create geometric forms that might be mistaken for artificial manufacture. The key to distinguishing natural concretions from artificial objects lies in understanding the formation processes and conducting appropriate chemical and structural analyses. Natural concretions typically show gradual compositional changes from center to rim, reflecting the conditions under which they formed. They often contain inclusions of the host rock and show crystal structures that reflect natural mineral growth processes. Artificial objects, by contrast, typically show evidence of manufacturing processes, tool marks, uniform compositions, crystal structures that reflect high-temperature processing, or alloy compositions that don't occur naturally. These signatures can be detected using electron microscopy, X-ray diffraction, and chemical analysis techniques. Another category of controversial artifacts involves objects allegedly found in coal seams. Coal forms from compressed organic matter over millions of years, so any objects found within coal deposits should theoretically be of similar age. Claims have been made for finding metal tools, jewelry, and even mechanical devices embedded in coal. Investigation of these claims typically reveals more mundane explanations. Objects can become embedded in coal during the mining process, when modern tools break and become mixed with the extracted coal. Coal seams are often fractured and can contain cavities where more recent objects can become lodged. The dating of coal seams themselves can be complex, particularly in areas where geological processes have disturbed the original stratigraphy. However, the coal context does raise interesting questions about preservation potential. The reducing chemical environment within coal deposits can preserve organic and metallic materials that would quickly decay under normal surface conditions. If artificial objects were somehow incorporated into forming coal deposits, they might indeed be preserved for millions of years. The challenge lies in establishing the true stratigraphic context of such finds. Simply being found in coal is not sufficient evidence of great age. The object must be demonstrably contemporaneous with the coal formation, which requires careful geological and radiometric analysis of the surrounding rock formations. The Antikythera mechanism represents a fascinating example of an artifact that initially seemed anachronistic, but proved to have a conventional, if surprising, explanation. Discovered in a Roman shipwreck off the Greek island of Antikythera, this complex bronze mechanism contained more than 30 meshing gears and appeared far too sophisticated for ancient Greek technology. Detailed analysis using X-ray tomography and computer modeling revealed that the mechanism was indeed an ancient Greek device created around 100 BCE. It functioned as an analog computer for predicting astronomical positions and eclipses, demonstrating a level of mechanical sophistication that historians had not previously attributed to ancient Greek craftsmen. The Antikythera mechanism illustrates an important principle in evaluating unusual artifacts. Our assumptions about past technological capabilities are often incomplete or incorrect. The discovery forced historians to revise their understanding of ancient Greek mechanical knowledge and reminded researchers to remain open to evidence that challenges conventional chronologies. This principle is particularly relevant to the search for evidence of ancient industrial civilizations. Our understanding of what technological signatures to expect is based largely on our own civilization's development path. Ancient civilizations that developed along different technological trajectories might have left signatures that we wouldn't recognize or that we would dismiss as natural phenomena. The question of distinguishing natural from artificial becomes even more complex when dealing with trace chemical signatures rather than physical objects. Modern analytical techniques can detect incredibly subtle chemical anomalies, but interpreting these anomalies requires deep understanding of both natural geochemical processes and potential technological signatures. Consider the problem of detecting ancient metallurgy in the geological record. Modern metal smelting creates distinctive patterns of trace element pollution that can be detected in sediment cores and ice sheets. But natural mineral deposits also contain elevated concentrations of metals, and natural weathering processes can redistribute these metals in ways that might mimic technological signatures. The key to distinguishing between natural and artificial metal enrichment lies in understanding the characteristic patterns created by each process. Natural mineral deposits typically show gradual compositional gradients that reflect the geological processes that concentrated the metals. Smelting operations, by contrast, create sharp chemical boundaries and distinctive ratios of trace elements that reflect the high-temperature processing conditions. The isotopic signatures of metals provide particularly sensitive indicators of artificial processing. Different ore deposits have characteristic isotopic compositions that reflect their geological formation. When metals from multiple sources are combined during smelting and alloying, they create isotopic mixtures that don't occur in natural deposits. Lead isotope ratios have proven particularly useful for tracing ancient metallurgical activities. Lead from different geological sources has distinctive isotopic signatures, allowing archaeologists to identify trade networks and technological practices of ancient civilizations. These signatures can be preserved in sediments and artifacts for thousands of years, providing a permanent record of metallurgical activities. The challenge of interpreting chemical anomalies becomes even more complex when dealing with very ancient time periods. Earth's geochemical cycles have evolved over geological time as the planet's atmosphere, oceans, and life forms have changed. Chemical signatures that might clearly indicate technological activity in recent sediments could be ambiguous or uninterpretable in very ancient rocks. For example, the oxygen content of Earth's atmosphere has varied dramatically over geological time. For most of Earth's history, atmospheric oxygen levels were much lower than today, which would have profoundly affected the preservation and chemical alteration of any technological artifacts. Materials that oxidize rapidly in today's atmosphere might be stable under ancient atmospheric conditions. Similarly, the evolution of life has fundamentally altered Earth's geochemical cycles. The development of photosynthesis, the evolution of shell-forming organisms, and the colonization of land by plants have all created major changes in how elements cycle through Earth systems. Chemical signatures that would be anomalous today might have been normal under ancient biological conditions. These complications emphasize the importance of understanding natural background variability when searching for evidence of ancient technological activity. Any potential technological signatures must be evaluated against the full range of natural processes that could have operated under ancient environmental conditions. The statistical analysis of geochemical data also presents challenges. With increasingly sensitive analytical techniques, scientists can detect smaller and smaller anomalies in natural systems. But not every anomaly indicates something significant. Some apparent patterns might simply reflect random variation or analytical artifacts. Distinguishing meaningful signals from noise requires sophisticated statistical methods and multiple independent lines of evidence. A single anomalous measurement might be dismissed as analytical error or natural variation, but multiple independent measurements showing coordinated anomalies would be much more difficult to explain without invoking some systematic cause. The preservation bias that affects all geological evidence is particularly problematic when searching for evidence of ancient technological activity. The materials and signatures most likely to preserve over geological time are not necessarily those that would provide the clearest evidence of intelligent manufacture. For example, the most durable materials, ceramics, stone, some metals under favorable conditions might preserve physical objects that could be recognized as artificial. But the most unambiguous technological signatures, complex organic compounds, electronic devices, precision-manufactured components would be unlikely to survive for millions of years. This preservation bias means that evidence of ancient technological civilizations, if it exists, might not take the forms we would expect based on our own technological experience. We might need to look for much more subtle signatures, isotopic anomalies, unusual mineral assemblages, or chemical compositions that indicate high-temperature processing. The ongoing development of new analytical techniques continues to expand our ability to detect and characterize potential evidence of ancient technological activity. Advanced mass spectrometry methods can measure isotope ratios with unprecedented precision. New techniques for analyzing organic compounds can detect trace concentrations of synthetic materials. Improved methods for characterizing mineral structures can reveal evidence of high-temperature or high-pressure processing. These advancing capabilities raise the intriguing possibility that we might eventually discover evidence of ancient technological activity that is currently below our detection threshold. As our analytical methods become more sensitive and our understanding of natural processes becomes more sophisticated, we might find that some phenomena we currently dismiss as natural actually reflect technological activity from the deep past. The search for evidence of ancient civilizations ultimately requires balancing appropriate skepticism with openness to unexpected discoveries. While most claimed anomalies have conventional explanations, the history of science is filled with examples of important discoveries that were initially dismissed as impossible or irrelevant. The key is applying rigorous analytical methods while remaining aware of the limitations of our current knowledge. Every anomalous finding deserves careful investigation, but extraordinary claims require extraordinary evidence. The goal is not to prove or disprove the existence of ancient technological civilizations, but to develop the methods and understanding necessary to recognize such evidence if it exists. The ocean. Preserver and destroyer. The ocean covers more than 70% of Earth's surface and extends to depths of over 11 kilometers, yet it remains one of the least explored regions of our planet. We have better maps of Mars than of our own ocean floor. This vast aquatic realm presents a paradox for those searching for traces of ancient civilizations. It is simultaneously Earth's greatest preserver of information and its most efficient destroyer of evidence. The ocean's dual nature, as preserver and destroyer, stems from the complex interplay of physical, chemical, and biological processes that operate in marine environments. On one hand, the deep ocean provides stable, low-energy conditions that can preserve materials for millions of years. The cold temperatures, high pressure, and reduced oxygen levels in deep marine sediments create ideal conditions for preservation. Some of our best records of ancient climate and environmental conditions come from deep ocean sediment cores. On the other hand, the ocean is in constant motion. Currents transport materials across entire ocean basins, Waves and tides constantly rework shallow marine sediments. Most dramatically, the process of plate tectonics gradually destroys the ocean floor itself, carrying sediments and any evidence they might contain down into Earth's interior to be recycled. This recycling process is remarkably efficient. The oldest ocean floor on Earth is only about 200 million years old young by geological standards. Everything older has been swallowed by subduction zones, where oceanic plates dive beneath continental plates and are consumed by the underlying mantle. Entire ancient oceans have disappeared without a trace, taking with them any evidence of coastal civilizations that might have existed on their shores. The implications for detecting ancient civilizations are profound. If technological societies developed primarily in coastal areas, as many human civilizations have done, their remains might be preferentially located in regions that are now underwater or have been completely destroyed by plate tectonic processes. The most accessible and fertile lands throughout Earth's history have often been coastal plains and river deltas, precisely the areas most vulnerable to sea level changes and geological recycling. Sea level itself has fluctuated dramatically throughout Earth's history. During ice ages, when vast amounts of water were locked up in continental glaciers, sea levels dropped by more than 100 meters below present levels. During warm periods, when ice sheets melted and thermal expansion increased ocean volume, sea levels rose far above current levels. These changes exposed and flooded vast areas of continental shelf, potentially burying or destroying evidence of coastal settlements. The most recent ice age provides a compelling example of how sea level changes can erase evidence of human activity. 20,000 years ago, at the height of the last glacial maximum, sea levels were about 120 meters lower than today. Vast areas of what is now ocean floor were dry land, including the Bering Land Bridge that connected Asia and North America, and extensive coastal plains around all continents. As the ice sheets melted over the following 10,000 years, these exposed areas were gradually flooded, burying any evidence of human occupation beneath hundreds of meters of water and marine sediment. Archaeological sites that might have provided crucial evidence of early human migration and cultural development now lie on the ocean floor, largely inaccessible to conventional archaeological investigation. Doggerland provides a particularly poignant example of this process. This now submerged landmass connected Britain to continental Europe during the last ice age, covering an area roughly the size of modern-day Britain. As sea levels rose following the ice age, Doggerland was gradually flooded, finally disappearing beneath the North Sea around 8,000 years ago. Archaeological evidence suggests that Doggerland was home to thriving human populations who exploited its rich hunting and fishing resources. Stone Age tools, human remains, and evidence of settlements have been recovered from the seafloor by fishing vessels and marine archaeological expeditions. But this evidence represents only a tiny fraction of what must have existed on this vast landmass. The submergence of Doggerland illustrates how entire regions of human occupation can be lost beneath rising seas. If similar flooding occurred during earlier periods of Earth's history, evidence of much older civilizations might now lie buried beneath hundreds of meters of water and sediment on continental shelves around the world. India's submerged city of Dwarka presents another intriguing example of how the ocean can preserve and conceal archaeological evidence. According to ancient texts, Dwarka was a magnificent city that sank beneath the sea after the death of Lord Krishna. For centuries, this was dismissed as mythology, but marine archaeological investigations have revealed extensive underwater structures off the coast of Gujarat that may represent the remains of an ancient urban center. The underwater ruins of Dwarka include stone walls, paved roads, and what appear to be the foundations of large buildings. Radiocarbon dating of artifacts recovered from the site suggests construction dates ranging from several thousand to over 9,000 years ago. While the interpretation of these findings remains controversial, they demonstrate that significant human settlements can indeed be preserved underwater for thousands of years. Similar underwater archaeological sites have been discovered around the world. The Mediterranean Sea contains numerous submerged settlements from various historical periods. The Black Sea, which was a freshwater lake, until rising sea levels broke through the Bosphorus around 7,000 years ago, has preserved remarkably well-preserved shipwrecks and coastal settlements in its oxygen-poor deep waters. These discoveries highlight both the potential for underwater preservation and the challenges of underwater investigation. The same conditions that can preserve archaeological materials, cold temperatures, high pressure, lack of oxygen, also make investigation extremely difficult and expensive. Advanced diving technology, remotely operated vehicles, and sophisticated sonar mapping systems are required to locate and study underwater sites. The preservation potential of marine environments varies dramatically with depth, temperature, and chemical conditions. Shallow coastal waters, while more accessible for investigation, are subject to wave action, storms, and bioturbation by marine organisms that can quickly destroy or bury archaeological materials. Deep ocean environments provide more stable conditions, but are largely inaccessible to conventional archaeological methods. The chemistry of seawater also affects preservation in complex ways. The high salt content can accelerate the corrosion of metals, while simultaneously preserving organic materials in some conditions. The pH of seawater affects the dissolution of carbonates and other minerals. The presence or absence of oxygen in marine sediments determines whether organic materials decay or are preserved as fossil carbon. Anaerobic conditions in deep marine sediments can preserve organic materials for millions of years. The Black Sea, with its oxygen-free deep waters, contains some of the best preserved ancient shipwrecks ever discovered. The wood remains intact, ropes and rigging are preserved, and even organic cargo can survive for thousands of years. These conditions demonstrate the remarkable preservation potential of marine environments when the chemistry is favorable. However, the vast majority of the ocean floor experiences conditions that are far less favorable for preservation. Bioturbation by bottom-dwelling organisms constantly reworks the upper layers of marine sediments, mixing and destroying stratigraphic relationships. Deep ocean currents can erode sediments and transport materials far from their original locations. Hydrothermal activity can alter the chemical composition of sediments and destroy preserved materials. The process of diagenesis, the physical and chemical changes that occur in sediments after deposition, can both preserve and destroy evidence over geological time. Under favorable conditions, diagenesis can replace original materials with stable minerals, creating fossils that preserve detailed structural information. Under unfavorable conditions, the same processes can completely dissolve and destroy organic and inorganic materials. The ocean's role as a carbon reservoir adds another layer of complexity to the preservation equation. The ocean contains roughly 50 times more carbon than the atmosphere, and this carbon cycles between different chemical forms over various timescales. Biological processes in the ocean can concentrate carbon into shells and skeletons that sink to the seafloor and become incorporated into sedimentary rocks. This carbon cycling means that evidence of ancient atmospheric changes, including those that might indicate technological activity, can be preserved in marine sediments for millions of years. The carbon isotope signatures created by fossil fuel combustion, for example, are being incorporated into marine carbonates and organic matter that will remain in ocean sediments long after our civilization ends. But the ocean's carbon system is also highly dynamic. Changes in ocean temperature, circulation, and chemistry can alter how carbon is distributed between different reservoirs. Ocean acidification, caused by the absorption of atmospheric carbon dioxide, is currently changing the chemistry of seawater in ways that could affect the preservation of carbonate materials. The deep ocean contains some of Earth's most extreme environments, including hydrothermal vents where superheated water rich in dissolved minerals creates unique ecosystems and preservation conditions. These environments can precipitate minerals rapidly, potentially encasing and preserving materials in ways that wouldn't occur elsewhere. Some researchers have speculated that hydrothermal environments might provide unusual opportunities for preserving evidence of technological activity. Conversely, the corrosive nature of hydrothermal fluids can also destroy materials rapidly. The high temperatures, acidic conditions, and reactive chemistry of these environments would quickly dissolve most artificial materials. Only the most chemically resistant materials would have any chance of preservation in such extreme conditions. The ocean also serves as the ultimate destination for much of the sediment eroded from continents. Rivers carry vast quantities of dissolved and suspended material to the sea, where it settles out in deltaic and deep marine environments. This sedimentation process can bury and preserve surface features, but it can also dilute and disperse any evidence of technological activity to concentrations below detection limits. The rate of marine sedimentation varies dramatically in different environments. Near river mouths and in areas of high biological productivity, sediments can accumulate rapidly, potentially preserving detailed records of environmental conditions. In the deep ocean, far from continental sediment sources, sedimentation rates are much slower, and the records are more temporally compressed but potentially more complete. These variable sedimentation rates have important implications for detecting ancient technological signatures. Rapid sedimentation might preserve high-resolution records of short-term environmental changes, including those that might indicate technological activity. Slow sedimentation might preserve longer-term trends, but could average out short-term signatures to the point where they become undetectable. The biological productivity of marine environments also affects preservation potential. High productivity areas create reducing conditions in sediments that can preserve organic materials, but they also create intense biological activity that can destroy other types of evidence. Low productivity areas have less biological activity, but also provide less organic matter to create favorable preservation conditions. Marine organisms themselves can both preserve and destroy evidence of past civilizations. Shell-forming organisms incorporate dissolved materials from seawater into their skeletons, potentially preserving chemical signatures of ancient environmental conditions. But marine borers can also destroy wooden structures and other organic materials, while bioturbation by bottom-dwelling organisms can mix and destroy stratigraphic records. The discovery of deep-sea mining activities has revealed how human technological activities are now extending into the deep ocean environment. These activities are creating new types of signatures in marine sediments, disturbed seafloor sediments, metal-rich tailings, and altered chemical compositions that will remain detectable for thousands to millions of years. The patterns created by deep-sea mining are distinctly different from natural seafloor processes. The linear tracks left by mining equipment, the altered grain size distributions of sediments, and the distinctive trace element compositions of mining waste create signatures that would be difficult to explain through natural processes alone. This modern example demonstrates how technological activities can create detectable signatures in marine environments, and raises the question of whether similar signatures might exist from ancient technological civilizations. If ancient civilizations engaged in marine resource extraction, trade, or waste disposal, they might have left distinctive signatures in marine sediments that could still be detectable today. The global circulation of ocean currents also affects how evidence of ancient civilizations might be preserved and distributed. Deep ocean currents transport materials across entire ocean basins over timescales of hundreds to thousands of years. Surface currents can carry floating debris to remote locations where it might be preserved in unusual environments. The Great Pacific Garbage Patch demonstrates how modern ocean circulation concentrates artificial materials in specific regions. These accumulation zones contain vast quantities of plastic debris and other artificial materials that are being gradually broken down by physical and biological processes. While current plastics would not survive over geological time, they do demonstrate how ocean circulation can concentrate technological debris in specific locations. If ancient technological civilizations produced materials that could survive ocean transport, similar accumulation zones might have concentrated evidence of their activities in specific marine environments. These zones might represent the most promising locations for searching for evidence of ancient technological activity in marine sediments. The study of marine sediment cores has revealed detailed records of past environmental changes that extend back millions of years. These cores contain evidence of climate changes, volcanic eruptions, asteroid impacts, and biological evolution. They also preserve evidence of recent human activities, including industrial pollution, nuclear testing, and changes in land use patterns. The techniques used to analyze marine sediment cores continue to improve, allowing scientists to detect increasingly subtle signals of past environmental changes. Advanced mass spectrometry can measure trace element concentration and isotope ratios with extraordinary precision. New methods for analyzing organic compounds can detect synthetic materials at extremely low concentrations. These advancing analytical capabilities raise the possibility that future investigations of marine sediments might reveal evidence of ancient technological activities that is currently below detection limits. As our understanding of natural marine processes improves and our analytical methods become more sensitive, we might discover anomalies in existing sediment core collections that indicate technological activity from the deep past. The ocean's role as both preserver and destroyer of evidence creates a complex landscape for searching for traces of ancient civilizations. While the ocean has undoubtedly destroyed vast amounts of evidence through plate tectonic recycling and erosional processes, it has also preserved detailed records of environmental conditions that extend back millions of years. The challenge lies in learning to read these marine archives with sufficient sophistication to distinguish between natural environmental changes and those that might indicate technological activity. This requires not only advanced analytical methods, but also a deep understanding of how natural marine systems operate over geological time. The ocean's vast unexplored regions represent a frontier for both archaeological investigation and the search for evidence of ancient civilizations. As technology advances and makes deep ocean exploration more feasible, we may discover that the ocean floor contains archives of Earth's history that we have barely begun to explore. The dual nature of the ocean as preserver and destroyer reminds us that absence of evidence is not evidence of absence. The ocean has swallowed entire continents worth of evidence about Earth's past, including potentially crucial information about ancient civilizations. What remains is a partial, biased sample that may not be representative of the full scope of intelligence that may have existed on our planet. Yet the ocean also offers hope. Its vast sedimentary archives contain detailed records that extend back far longer than any terrestrial records. If evidence of ancient technological civilizations exists anywhere in the geological record, the deep marine environment represents one of our best chances of finding and preserving it. The challenge is learning how to look in the right places and recognize the signatures when we find them. The chemistry of civilization in the grand theater of geological time. Civilizations may rise and fall like brief flickers of light, but their chemical signatures can persist like echoes in stone, water, and ice long after their creators have vanished. If we are to understand what traces ancient civilizations might leave behind, we must first understand the most fundamental question: which materials and processes create the most durable signatures in Earth's chemical systems? The answer lies not in the grand monuments or sophisticated technologies that define civilizations in human terms, but in the mundane byproducts of industrial processes, the waste streams of manufacturing, and the subtle alterations to natural cycles that technological societies inevitably create. These chemical fingerprints, invisible to the naked eye but detectable by modern analytical instruments, represent the most likely evidence that future investigators might find of our own civilization, and that we might find of civilizations that came before. Plastics occupy a unique position in the hierarchy of civilization's chemical legacy. These synthetic polymers, created through industrial processes that don't occur in nature, represent one of the clearest signatures of technological sophistication. Since the 1950s, humans have produced over 9 billion tons of plastic materials, distributed these synthetic compounds across every environment on Earth, from the deepest ocean trenches to the highest mountain peaks. The durability of plastics in the environment has become legendary, but their long-term preservation potential is more complex than popular understanding suggests. Under surface conditions, exposed to ultraviolet radiation, temperature fluctuations, and biological activity, most plastics break down within decades to centuries. The process begins with photodegradation, where ultraviolet light breaks the polymer chains into smaller fragments. Mechanical weathering then reduces these fragments to microscopic particles that can be dispersed by wind and water. However, under the right conditions, plastic materials can persist for much longer periods. Buried in sediments, protected from light and oxygen, some synthetic polymers could potentially survive for thousands of years. The chemical bonds in certain plastics are extremely stable, requiring specific catalysts or extreme conditions to break down completely. More importantly, the breakdown products of plastics create distinctive chemical signatures that could persist even longer than the original materials. When plastics degrade, they release characteristic organic compounds, trace metals from additives and fillers, and isotopic signatures that reflect their industrial origins. These molecular fossils of the plastic age could remain detectable in sediments and ice cores for thousands to tens of thousands of years. The global distribution of plastic pollution creates a unique stratigraphic marker that would be recognizable to future geologists. The rapid increase in plastic production since 1950 has created a distinctive layer in recent sediments that contains synthetic polymer fragments, associated additives, and characteristic isotopic signatures. This plastic horizon represents one of the clearest chemical boundaries that our civilization is creating in the geological record. Ceramics represent another category of materials with exceptional preservation potential. The high-temperature processing required to create ceramic materials produces crystal structures and chemical compositions that are extremely stable under geological conditions. Ancient pottery shards represent some of the most durable artifacts from early civilizations, surviving burial in soils and sediments for thousands of years with minimal alteration. Modern industrial ceramics, created at even higher temperatures and with more controlled compositions, would likely preserve even better than traditional pottery. Advanced ceramics used in electronics, aerospace applications, and industrial processes often contain rare elements and distinctive isotopic signatures that would be virtually impossible to produce through natural processes. The widespread use of ceramic materials in modern infrastructure creates another potential marker of our technological civilization. Concrete, while often considered a simple building material, is actually a complex ceramic composite whose chemical composition reflects the industrial processes used in its manufacture. The isotopic signatures of the limestone and other raw materials used in cement production create distinctive chemical fingerprints that can be traced to specific geological sources and industrial facilities. Rare earth elements present perhaps the most unambiguous chemical signature of advanced technological civilization. These elements, including neodymium, europium, terbium, and dozens of others, are essential components of modern electronics, but occur in extremely low concentrations in Earth's crust. Natural processes rarely concentrate these elements to significant levels, and their distinctive geochemical properties make them excellent tracers of industrial activity. Modern electronics manufacturing has created unprecedented concentrations of rare earth elements in specific locations around the world. Mining and processing facilities, electronics manufacturing centers, and electronic waste disposal sites all contain elevated levels of these elements in patterns that would be difficult to explain through natural processes alone. The isotopic signatures of rare earth elements provide even more definitive evidence of technological processing. Different ore deposits have characteristic isotopic compositions that reflect their geological origins. When rare earth elements from multiple sources are combined during industrial processing, they create isotopic mixtures that simply don't occur in nature. Perhaps most significantly, the global distribution of rare earth elements in modern sediments reflects the patterns of international trade, manufacturing, and waste disposal that characterize our technological civilization. These distribution patterns, preserved in lake sediments, river deposits, and marine cores, create a distinctive chemical signature that would remain detectable for millions of years. Nuclear isotopes represent the ultimate signature of advanced technological capability. The artificial isotopes created by nuclear reactors and weapons testing are so rare in nature that their presence serves as an unambiguous indicator of technological activity. Plutonium-239, for example, is produced almost exclusively by nuclear reactors and weapons programs. Its detection in environmental samples provides definitive proof of nuclear technology. The global distribution of artificial isotopes from atmospheric nuclear testing during the 1950s and 1960s has created a distinctive layer in sediment cores and ice sheets worldwide. This nuclear signature will remain detectable for hundreds of thousands of years, serving as a permanent marker of our technological age. Future investigators examining sediment cores would find a sharp spike in radioactive isotopes corresponding to our period of nuclear weapons testing. But the nuclear signature extends beyond weapons testing. Nuclear power plants alter the isotopic composition of uranium and create complex mixtures of fission products that don't occur naturally. Even the medical use of radioactive isotopes creates distinctive signatures that can be detected in wastewater treatment facilities and hospital waste disposal sites. The chemistry of agriculture represents a more subtle but equally significant signature of civilizational development. The large-scale application of synthetic fertilizers has fundamentally altered the nitrogen cycle in ways that create detectable chemical signatures in soils, groundwater, and marine sediments. The industrial production of ammonia for fertilizers requires high temperatures and pressures that create characteristic isotopic signatures in the nitrogen compounds. The Haber-Bosch process, which converts atmospheric nitrogen into ammonia for fertilizer production, has doubled the amount of biologically available nitrogen in Earth's ecosystems. This massive perturbation to a fundamental biogeochemical cycle creates nitrogen isotope signatures that differ dramatically from natural nitrogen cycling. These signatures are being incorporated into plant tissues, soil, organic matter, and sedimentary deposits around the world. Agricultural practices also redistribute trace elements in characteristic patterns. The mining and application of phosphate fertilizers concentrates naturally rare elements like uranium, thorium, and various heavy metals in agricultural soils. These concentration patterns reflect the industrial supply chains and application practices of modern agriculture rather than natural geological processes. The ecological footprint of civilization extends beyond direct chemical signatures to include the biological and environmental changes that technological societies inevitably create. The extinction of species, the introduction of non-native organisms, and the alteration of ecosystem structures all leave traces that can persist in the fossil record for millions of years. Mass extinctions create distinctive patterns in the fossil record that remain detectable for hundreds of millions of years. The current extinction event, often called the sixth mass extinction, is creating patterns of species loss that will be recognizable to future paleontologists. The selective nature of modern extinctions affecting large-bodied species, island species, and species with small populations creates a distinctive signature that differs from natural extinction patterns. The introduction of domesticated species and non-native organisms creates another type of biological signature. Domestic animals and plants have been dispersed far from their natural ranges, creating biogeographical patterns that would be difficult to explain without invoking intelligent intervention. The bones of domestic animals in archaeological sites provide clear evidence of human activity, and similar patterns might indicate the activities of ancient technological civilizations. The concept of industrial fossils represents a new category of evidence that our civilization is creating for future investigators. These are not traditional fossils of once-living organisms, but rather the mineralized remains of industrial processes and technological artifacts. When metallic objects corrode in soil, they create distinctive mineral assemblages that preserve the shape and composition of the original artifacts. Industrial slag, the waste product of metal smelting, creates unique mineral compositions that don't occur in natural geological processes. These artificial rocks contain characteristic combinations of elements and minerals that reflect the high temperature, reducing conditions used in metallurgical processes. The isotopic compositions of metals in industrial slag also preserve information about the ore sources and processing methods used by ancient metallurgists. Even the waste products of modern industry create potential fossils for future discovery. Landfills contain stratified sequences of technological debris that chronicle the development of industrial civilization. While most organic materials in landfills decay rapidly, metals, ceramics, and synthetic materials can persist in recognizable forms for thousands of years. The chemical alterations created by acid mine drainage represent another type of industrial fossil. Mining operations often expose sulfide minerals to water and oxygen, creating acid solutions that dissolve metals and create distinctive mineral precipitates. These acid mine drainage signatures can persist in soils and sediments for thousands of years, creating chemical markers of mining activity long after the mines themselves have been abandoned. Urban geochemistry has emerged as a new field of study focused on understanding how cities alter the chemical composition of their surrounding environments. Urban soils contain elevated levels of lead from gasoline and paint, elevated levels of various trace metals from industrial activities, and distinctive isotopic signatures that reflect the materials and energy sources used in urban environments. The heat island effect created by cities also leaves subtle but detectable signatures in the geological record. Urban areas are typically several degrees warmer than surrounding rural areas due to the absorption of solar radiation by pavement and buildings, and the release of waste heat from energy consumption. This temperature difference affects the isotopic composition of precipitation and can be preserved in tree rings and sediment records. The hydrological impacts of urbanization create distinctive signatures in stream sediments and groundwater systems. Urban runoff carries characteristic pollutants including road salts, automotive fluids, and various synthetic chemicals. The altered flow patterns created by urban drainage systems also create distinctive sedimentary signatures that differ from natural stream systems. Transportation networks create linear chemical signatures that reflect the materials and energy sources used in their construction and operation. Roads concentrate wear particles from tires and brake systems, creating elevated levels of zinc, copper, and various organic compounds along transportation corridors. These linear geochemical anomalies would be recognizable to future investigators as evidence of systematic transportation systems. The chemical signatures of energy production and consumption represent perhaps the most pervasive markers of technological civilization. The combustion of fossil fuels creates distinctive carbon isotope signatures that are being incorporated into all carbon-bearing materials at Earth's surface. Coal, oil, and natural gas each have characteristic isotopic compositions that reflect their geological origins and the conditions under which they formed. The large-scale extraction and combustion of fossil fuels has created a global carbon isotope anomaly that will remain detectable in sedimentary rocks for millions of years. This fossil fuel signature represents one of the clearest chemical markers of our industrial civilization and demonstrates how energy use can create permanent alterations to Earth's chemical systems. Alternative energy systems also create distinctive chemical signatures. Solar panels contain high concentrations of silicon, silver, and various rare metals in configurations that don't occur naturally. Wind turbines require large quantities of rare earth elements for their permanent magnets. Even hydroelectric systems create distinctive chemical signatures through the altered water chemistry and sediment transport patterns in reservoir systems. The processing of materials for technological applications creates distinctive signatures that persist long after the original applications have ended. The beneficiation of metal ores concentrates naturally rare elements and creates waste streams with unusual chemical compositions. The production of semiconductors requires ultra-pure materials and creates distinctive patterns of trace element distribution. The chemical signatures of modern civilization are not distributed randomly across Earth's surface, but reflect the economic, political, and technological systems that created them. Industrial centers contain much higher concentrations of technological signatures than rural areas. Transportation networks create linear patterns of chemical alteration. Mining regions contain distinctive signatures of resource extraction and processing. These spatial patterns of chemical alteration provide important clues for understanding how technological civilizations interact with their environments. If ancient technological civilizations followed similar patterns of development, their chemical signatures might be concentrated in specific types of locations near resource deposits, along transportation corridors, or in areas with favorable environmental conditions for industrial development. The chemistry of civilization ultimately reflects the fundamental thermodynamic requirements of technological development. All technological processes require energy inputs and produce waste outputs. The laws of thermodynamics ensure that these processes leave permanent traces in Earth's chemical systems, even if the civilizations that created them eventually disappear. Understanding these chemical signatures provides a roadmap for detecting evidence of ancient technological civilizations. Rather than looking for preserved artifacts or ruins, future investigators should focus on the subtle chemical alterations that any technological civilization would necessarily create. These molecular fossils of ancient industry might represent our best hope for detecting evidence of intelligence in Earth's deep past. The chemical legacy of our own civilization serves as both a warning and a guide. The permanent alterations we're creating in Earth's chemical systems will persist long after our cities crumble and our machines rust away. Future investigators will judge our civilization not by our monuments or achievements, but by the chemical signatures we leave behind. The question remains, are we the first to leave such signatures, or are we simply the latest in a long series of technological experiments that Earth has witnessed throughout its vast history? Myths and cultural memory, deep within the collective memory of human cultures, lies a remarkable consistency of themes that span continents and millennia. Stories of great floods that destroy civilizations, of lands that sink beneath the waves, of golden ages that end in catastrophe, of advanced peoples who possessed knowledge and capabilities that were subsequently lost. These narratives, dismissed by many as mere mythology, may actually preserve echoes of real geological events, and possibly even memories of civilizations far older than our written records suggest. The universality of flood myths across human cultures presents one of the most intriguing puzzles in anthropology and archaeology. From the biblical account of Noah's Ark to the Mesopotamian epic of Gilgamesh, from Hindu Puranas describing cosmic deluges to Native American legends of world-destroying floods, virtually every culture on Earth preserves stories of catastrophic flooding that destroys earlier civilizations and forces survivors to rebuild their societies from scratch. The conventional explanation for these flood myths focuses on local or regional flooding events that were catastrophic enough to be preserved in cultural memory and gradually transformed into cosmic narratives through repeated telling. The Black Sea deluge hypothesis, for example, suggests that the rapid flooding of the Black Sea basin around 7,600 years ago might have inspired flood stories that spread throughout the ancient world through migration and cultural exchange. Archaeological evidence supports the reality of significant flooding events throughout human history. The Mediterranean experienced dramatic sea level changes during the Messinian salinity crisis, when the sea nearly dried up completely around 5 million years ago, before being catastrophically refilled. More recently, the rapid melting of ice sheets at the end of the last glacial period caused sudden flooding events that would have been catastrophic for any human populations living in low-lying areas. The channeled scablands of eastern Washington provide dramatic evidence of catastrophic flooding on a scale almost beyond imagination. These landscapes were carved by repeated megafloods when ice dams failed and released the entire contents of glacial Lake Missoula in a matter of days. The flood waters, carrying house-sized boulders, carved channels hundreds of feet deep through solid basalt and created temporary waterfalls higher than Niagara Falls. Such geological catastrophes occurred repeatedly throughout the Ice Age, as climate fluctuations caused ice sheets to advance and retreat, creating temporary lakes that periodically burst their boundaries in devastating floods. If human populations witnessed these events, the memory would certainly be preserved in oral traditions and might well be transformed over time into stories of world-destroying deluges sent by angry gods. But the consistency of flood myths across cultures that had no historical contact with each other suggests that these stories might reflect something more than shared psychological archetypes or diffusion from a common source. The specific details that recur in flood narratives, the survival of a small group of people who preserve knowledge and restart civilization, the association with divine judgment or cosmic renewal, the emphasis on the loss of advanced knowledge suggests that these myths might preserve actual historical memories. The time depth of human oral tradition has been dramatically underestimated by Western scholarship. Recent research on Australian Aboriginal oral traditions has demonstrated that accurate geographical and ecological information can be preserved in oral narratives for over 10,000 years. Stories describing coastlines and landscapes that existed before post-glacial sea level rise have been shown to accurately describe conditions that haven't existed for hundreds of human generations. If oral traditions can preserve accurate information for 10,000 years, it's conceivable that they might preserve distorted but recognizable memories of events that occurred even earlier in human history. The flood myths might represent cultural memories of the rapid environmental changes that occurred during deglaciation, when sea levels rose by over 100 meters and vast areas of coastal land were flooded permanently. More speculatively, these myths might preserve memories of even more ancient events, perhaps civilizations that flourished during earlier interglacial periods and were destroyed by the onset of ice ages or other catastrophic environmental changes. The cyclical nature of glacial and interglacial periods means that Earth has experienced dozens of major climate transitions over the past few million years, each of which could have destroyed existing civilizations and forced survivors to rebuild their societies. Legends of lost continents and sunken cities present another category of myths that might preserve historical memories of real geological events. The story of Atlantis, as recorded by Plato, describes an advanced maritime civilization that sank beneath the ocean in a single day and night of catastrophe. While most scholars interpret Atlantis as a philosophical allegory rather than historical fact, similar stories appear in cultures around the world. Tamil literature describes Kumari Kandam, a lost continent that once connected India and Sri Lanka before being swallowed by the sea. Hindu texts describe Dwarka, Krishna's magnificent city that sank beneath the ocean after his death. Celtic mythology tells of Lyoness, a fertile land that lay between Cornwall and the Isles of Scilly before being overwhelmed by the sea. Japanese folklore describes similar lost lands beneath the Pacific Ocean. The remarkable consistency of these sunken land narratives across independent cultural traditions suggests that they might reflect real experiences of sea level change and coastal flooding. During the last ice age, sea levels were indeed over 100 meters lower than today, exposing vast continental shelf areas that are now underwater. These exposed areas included land bridges between continents and extensive coastal plains that would have been attractive for human settlement. As the ice sheets melted and sea levels rose, These exposed areas were gradually flooded, forcing human populations to migrate inland. The process was not always gradual. Periods of rapid ice sheet collapse could raise sea levels by several meters in just a few decades, creating catastrophic flooding events that would certainly be preserved in cultural memory. The archaeological record provides tantalizing hints that some of these flood legends might have historical foundations. Underwater archaeology has revealed submerged settlements around the world, from the Neolithic villages beneath the Black Sea to the prehistoric sites off the coasts of India, Japan, and the Mediterranean. These discoveries demonstrate that human populations did indeed occupy areas that are now underwater, and that evidence of their civilizations has been preserved beneath the sea. The city of Dwarka, mentioned in Hindu texts as Krishna's capital, has been the subject of intensive underwater archaeological investigation. The remains of stone structures, harbor works, and what appear to be planned urban layouts have been discovered on the seafloor off the coast of Gujarat. While the dating and interpretation of these remains is still controversial, they demonstrate that significant human settlements can indeed be preserved underwater for thousands of years. The concept of lost golden ages appears in virtually all cultural traditions, and might reflect historical memories of periods when human societies achieved higher levels of technological or social development before being disrupted by environmental changes or other catastrophes. The Greek concept of successive ages of gold, silver, bronze, and iron describes a decline from an original state of perfection. Hindu cosmology describes similar cycles of creation and destruction, spanning vast periods of time. These cyclical narratives might reflect the reality of how civilizations develop, flourish, and collapse in response to environmental changes and resource depletion. Archaeological evidence demonstrates that many ancient civilizations did indeed rise to considerable heights of achievement before collapsing due to climate change, resource exhaustion, or other factors. The Maya Classic period, the Bronze Age civilizations of the Eastern Mediterranean, and the Indus Valley civilization all represent examples of advanced societies that collapsed and were partially forgotten by later generations. The preservation of technical knowledge in mythological form presents another intriguing aspect of cultural memory. Many traditional cultures preserve surprisingly accurate astronomical knowledge in the form of mythological narratives and ritual practices. Ancient stone circles and other monuments demonstrate sophisticated understanding of celestial mechanics that was encoded in myths and religious practices rather than written technical manuals. The precision of this preserved astronomical knowledge suggests that other types of technical information might also be preserved in mythological form. Stories of magical objects that seem to describe advanced technologies, narratives about divine beings who possess seemingly impossible capabilities, and legends of lost arts and sciences might represent distorted but recognizable descriptions of actual technological achievements. The cargo cult phenomenon observed in the Pacific during the 20th century demonstrates how contact with advanced technology can be transformed into religious and mythological narratives within a few generations. Indigenous peoples who encountered modern aircraft and military equipment during World War II developed elaborate ritual systems designed to bring back the cargo and the advanced beings who had brought it. If similar processes occurred in the distant past, contact between less advanced populations and more technologically sophisticated civilizations might have been preserved in the form of myths about gods, angels, or other supernatural beings who possessed advanced capabilities. The remarkable consistency of certain mythological themes, flying vehicles, powerful weapons, advanced construction techniques, Sophisticated knowledge systems might reflect actual encounters with more advanced civilizations rather than purely imaginative constructs. The challenge lies in distinguishing between genuine historical memories, preserved in mythological form, and universal psychological archetypes that appear in all human cultures, regardless of historical experience. Carl Jung's concept of the collective unconscious suggests that certain mythological themes reflect fundamental patterns of human psychology, rather than historical memories of actual events. However, the specific geographical and technical details that appear in many traditional narratives suggest that at least some mythological content derives from historical experience, rather than purely psychological sources. The accuracy of oral traditions in preserving information about post-glacial environmental changes demonstrates that human cultures are capable of maintaining historical memories over extremely long periods. The process by which historical events become transformed into mythological narratives is complex and not well understood. Real events become embellished with supernatural elements, compressed in time, combined with other narratives, and interpreted through the cultural frameworks of successive generations. The original historical content may become virtually unrecognizable, yet certain core elements might still preserve accurate information about past events. Modern research into the relationship between geology and mythology has revealed surprising correlations between traditional stories and actual geological events. Aboriginal Australian traditions accurately describe volcanic eruptions and landscape changes that occurred thousands of years ago. Pacific Islander navigational traditions preserve detailed knowledge of ocean currents, weather patterns, and island distributions that would have been essential for long-distance voyaging. The emerging field of geomythology seeks to identify geological events that might have inspired mythological narratives. Volcanic eruptions, earthquakes, tsunamis, and other catastrophic events often leave distinctive signatures in both the geological record and cultural traditions. By comparing the timing and characteristics of known geological events with the details of traditional narratives, researchers are beginning to identify specific historical events that might have inspired particular myths. The implications for understanding ancient civilizations are significant. If cultural traditions can preserve memories of geological events and environmental changes over thousands of years, they might also preserve memories of human societies that flourished during earlier periods. The consistent themes of lost civilizations, advanced knowledge, and catastrophic destruction that appear in mythologies around the world might reflect actual historical experiences rather than purely imaginative constructs. The thin line between myth and historical memory becomes particularly important when considering the possibility of very ancient civilizations that might have existed during earlier geological periods. If technological civilizations arose and collapsed during previous interglacial periods or other favorable environmental windows, the memories of these societies might have been preserved in oral traditions and gradually transformed into the mythological narratives we observe today. The study of cultural memory and its relationship to geological events represents a frontier where archaeology, anthropology, geology, and psychology intersect. As our understanding of how information is preserved and transmitted through oral traditions improves, we may discover that humanity's mythological heritage contains far more historical content than previously suspected. The flood myths, lost continent legends, and golden age narratives that appear in cultures around the world might represent humanity's collective memory of a far more complex and interesting past than our written records suggest. If so, these stories might provide clues for understanding not only the history of our own species, but also the possibility that other intelligent civilizations might have risen and fallen on Earth during the vast expanse of geological time. Science, skepticism, and curiosity science operates as humanity's most powerful tool for distinguishing between what we wish were true and what actually is true. In the realm of investigating possible ancient civilizations, this distinction becomes particularly crucial, as the subject lies at the intersection of legitimate scientific inquiry and unfounded speculation. The challenge for researchers is maintaining the delicate balance between healthy skepticism that prevents the acceptance of extraordinary claims without extraordinary evidence, and the intellectual openness necessary to seriously investigate possibilities that challenge conventional understanding. The scientific method provides a structured approach for evaluating claims about ancient civilizations. Hypotheses must be testable, predictions must be falsifiable, and evidence must be reproducible and subject to peer review. These standards have served science well in distinguishing between legitimate discoveries and wishful thinking, but they also create challenges when investigating phenomena that exist at the limits of detectability or that require interdisciplinary expertise to properly evaluate. The Silurian hypothesis, as proposed by Schmidt and Frank, represents an exemplar of how to approach unconventional questions scientifically. Rather than claiming that ancient industrial civilizations definitely existed, the authors asked what evidence such civilizations would leave behind, and whether that evidence would be detectable using current methods. This approach transforms speculation into testable science by creating specific predictions that can be evaluated against empirical data. The hypothesis demonstrates how scientific thinking can illuminate new possibilities while maintaining rigorous standards of evidence. By grounding their investigation in established knowledge of geological processes, climate systems, and geochemistry, Schmidt and Frank created a framework for investigating ancient civilizations that could be evaluated using conventional scientific methods. Their work shows that asking unconventional questions doesn't require abandoning scientific rigor. However, the boundary between legitimate scientific inquiry and pseudoscientific speculation is not always clear, particularly when dealing with incomplete evidence and complex systems that are not fully understood. The history of archaeology and geology includes numerous examples of ideas that were initially dismissed as pseudoscientific, but were later validated by additional evidence. The theory of continental drift, the reality of catastrophic mass extinctions, and the role of asteroid impacts in Earth's history were all initially rejected by mainstream science before being accepted based on accumulating evidence. Conversely, the history of these fields also includes numerous examples of ideas that initially seemed promising, but were ultimately shown to be unfounded. 19th-century theories about lost Atlantean civilizations, early 20th-century ideas about canals on Mars, and various claims about ancient astronauts have all been thoroughly debunked by subsequent research. The challenge lies in distinguishing between ideas that are temporarily rejected due to insufficient evidence and those that are fundamentally flawed. This distinction requires careful evaluation of the quality of evidence, the logical consistency of proposed explanations, and the degree to which new ideas fit within established scientific knowledge. Pseudo-archaeology represents a particular concern when investigating possible ancient civilizations. This field includes claims about advanced ancient technologies, extraterrestrial visitors, lost continents, and other extraordinary phenomena that are typically supported by selective interpretation of evidence, logical fallacies, and rejection of mainstream scientific methods. While some pseudo-archaeological claims might contain grains of truth, the methodology used to support these claims undermines their credibility and makes it difficult to separate valid observations from unfounded speculation. The appeal of pseudo-archaeological explanations stems partly from their ability to provide simple answers to complex questions. Rather than acknowledging the limitations of current knowledge or the complexity of ancient societies, pseudo-archaeological theories often invoke extraordinary explanations that seem to resolve all mysteries at once. Ancient astronauts can explain any technological achievement that seems too advanced for its time period. Lost supercivilizations can account for any similarities between geographically separated cultures. These explanations have an intuitive appeal, but they fail to meet the standards of scientific evidence. They typically rely on selective citation of evidence, dismissal of contradictory data, and logical fallacies such as the argument from incredulity, the assumption that if something seems too difficult or unlikely to be achieved by ancient peoples, it must have had a supernatural or extraterrestrial explanation. The dangers of pseudo-archaeological thinking extend beyond simple factual errors. These approaches can reinforce racist assumptions about the capabilities of ancient peoples, particularly non-European cultures. When the achievements of Maya astronomers, Egyptian engineers, or Pacific Islander navigators are attributed to extraterrestrial intervention rather than human intelligence and creativity, it diminishes the actual accomplishments of these cultures and perpetuates harmful stereotypes. Furthermore, pseudo-archaeological thinking can undermine public understanding of how science works and how knowledge is validated. By promoting explanations that bypass the normal processes of peer review, replication, and critical evaluation, pseudo-archaeology can erode public trust in legitimate scientific institutions and methods. However, the existence of pseudo-archaeology should not prevent legitimate scientific investigation of unconventional possibilities. The key is applying appropriate scientific methods to evaluate extraordinary claims while remaining open to evidence that might challenge conventional understanding. This requires distinguishing between the methods used to investigate claims and the content of the claims themselves. A claim might seem extraordinary or unlikely, but if it can be investigated using rigorous scientific methods, it deserves serious consideration. The Silurian hypothesis exemplifies this approach. The possibility of ancient industrial civilizations might seem unlikely, but it can be investigated using established geological and geochemical methods. The interdisciplinary nature of research into ancient civilizations creates additional challenges for maintaining scientific rigor. Understanding the possible traces of ancient technological civilizations requires expertise in geology, geochemistry, climatology, archaeology, biology, and other fields. Few individual researchers possess all the necessary knowledge, which creates opportunities for misinterpretation and errors. Collaborative research involving experts from multiple disciplines provides the best approach for addressing these challenges. When geologists, archaeologists, chemists, and other specialists work together, they can provide the breadth of expertise necessary to properly evaluate complex questions about ancient civilizations. This collaborative approach helps ensure that all relevant factors are considered, and that conclusions are based on comprehensive analysis rather than narrow disciplinary perspectives. The role of technology in advancing the search for ancient civilizations cannot be understated. New analytical methods are constantly expanding our ability to detect subtle signatures of past human activity. Advanced mass spectrometry can measure isotope ratios with unprecedented precision. New methods for analyzing organic compounds can detect trace concentrations of synthetic materials. Improved statistical methods can identify patterns in complex datasets that might otherwise be dismissed as noise. These technological advances create new opportunities for investigating ancient civilizations, but they also create new challenges for interpreting data. As analytical sensitivity improves, researchers must become increasingly sophisticated about distinguishing between meaningful signals and background variation. The risk of false discoveries increases as the number of potential measurements grows, requiring more stringent statistical methods to avoid spurious conclusions. The temporal aspect of scientific progress also affects how claims about ancient civilizations are evaluated. Evidence that seems insufficient to support extraordinary claims today might become compelling as new analytical methods are developed and additional data are collected. This temporal dimension requires researchers to remain open to the possibility that current conclusions might be revised as knowledge advances. The history of science provides numerous examples of important discoveries that were initially rejected due to insufficient evidence or incompatibility with existing theoretical frameworks. The bacterial origin of stomach ulcers, the reality of meteorite impacts, and the existence of extrasolar planets were all initially dismissed before being validated by additional research. This historical perspective suggests that current skepticism about ancient civilizations should be tempered by recognition that scientific knowledge is provisional and subject to revision based on new evidence. While extraordinary claims require extraordinary evidence, the definition of what constitutes sufficient evidence may change as analytical capabilities improve and theoretical understanding develops. The social and cultural context in which scientific research occurs also influences how claims about ancient civilizations are received. Research that challenges established historical narratives or suggests that human capabilities are greater than previously recognized may encounter resistance that goes beyond purely scientific considerations. Cultural attachments to particular views of the past can influence how evidence is interpreted and what questions are considered worth investigating. Funding considerations also affect the direction of research into ancient civilizations. Research that challenges conventional understanding or investigates highly speculative possibilities may have difficulty obtaining funding from traditional sources. This creates a bias toward more conventional research topics and may limit investigation of potentially important but unconventional possibilities. Despite these challenges, the scientific investigation of possible ancient civilizations remains worthwhile for several reasons. First, the questions involved are inherently important for understanding human history and our place in the broader context of life on Earth. If technological civilizations have arisen and fallen multiple times during Earth's history, this would fundamentally change our understanding of intelligence, technology, and the long-term prospects for civilization. Second, the investigation of ancient civilizations provides valuable insights into the relationship between civilizations and their environmental impacts. By studying how our own civilization is altering Earth's chemical and biological systems, we can better understand what signatures past civilizations might have left behind and what our own long-term legacy might be. Third, the search for ancient civilizations drives the development of new analytical methods and theoretical frameworks that have applications beyond the specific question of ancient technological societies. Research into geochemical signatures of industrial activity, for example, has applications for understanding modern environmental problems and monitoring compliance with environmental regulations. Fourth, the interdisciplinary nature of research into ancient civilizations promotes collaboration between different scientific fields and encourages researchers to think broadly about complex problems. This cross-disciplinary fertilization can lead to insights and discoveries that might not emerge from more narrowly focused research. The question of ancient civilizations ultimately represents a frontier where established science meets the unknown. The challenge is exploring this frontier using rigorous scientific methods, while remaining open to discoveries that might challenge conventional understanding. This requires maintaining the delicate balance between skepticism and curiosity that lies at the heart of all scientific progress. The scientific investigation of possible ancient civilizations embodies the best traditions of scientific inquiry, asking important questions, developing testable hypotheses, applying rigorous methods, and remaining open to unexpected discoveries. Whether or not ancient technological civilizations actually existed on Earth, the process of investigating this possibility advances our understanding of geological processes, environmental change, and the long-term relationship between intelligence and planetary systems. Science succeeds not by accepting or rejecting extraordinary claims based on preconceptions, but by developing and applying methods that can reliably distinguish between valid and invalid hypotheses. The question of ancient civilizations provides an excellent opportunity to demonstrate and refine these methods while investigating one of the most fascinating possibilities in the history of our planet. Final reflection as we reach the end of our journey through deep time, examining the possibility that we were not the first technological civilization to arise on Earth, we find ourselves confronting profound questions not just about the past, but about our own future and the ultimate meaning of intelligence in the cosmos. The Silurian hypothesis, whether proven or disproven, forces us to consider our own legacy and what traces we will leave for future investigators to discover. Standing at this moment in history, we are creating an unprecedented footprint on our planet. Our industrial civilization is altering Earth's chemical systems, climate patterns, and biological communities in ways that will persist for millions of years. The carbon dioxide we're adding to the atmosphere will influence Earth's climate for hundreds of thousands of years. The artificial isotopes we've created will decay according to immutable physical laws, serving as cosmic clocks that mark our brief moment in Earth's vast timeline. The plastic waste we've distributed throughout the environment, the metals we've extracted and refined, the rare earth elements we've concentrated and dispersed, the nitrogen we've fixed, and the carbon we've mobilized, all of these create chemical signatures that will remain detectable long after our cities have crumbled and our machines have rusted away. We are writing our civilization's story not in monuments of stone, but in the molecular structure of Earth systems themselves. This realization carries both sobering responsibility and unexpected hope. The responsibility lies in recognizing that our current actions are creating a permanent legacy that will outlast everything we consider important about our civilization. Future investigators will judge us not by our art, our philosophy, or our scientific achievements, but by the chemical signatures we leave behind. They will see evidence of massive fossil fuel combustion, extensive mining operations, nuclear weapons testing, and industrial pollution long before they find any trace of our literature or our monuments. But there is hope in this perspective as well. If we are indeed leaving such persistent traces, then perhaps others before us did the same. The absence of obvious archaeological evidence for ancient technological civilizations may simply reflect the efficiency with which geological time erases the obvious traces of intelligence, while preserving the subtle chemical signatures that require sophisticated analysis to detect. The question of whether we are temporary passengers on Earth, like hypothetical previous civilizations, touches the deepest concerns about humanity's long-term survival. Our species has existed for only a few 100,000 years, an eye blink in geological time. Our technological civilization spans merely a few centuries. From the perspective of deep time, our entire existence appears as a brief flicker of activity that could easily disappear without leaving obvious traces for future investigators. This temporal perspective is both humbling and liberating. It reminds us that our problems, conflicts, and achievements, however important they seem to us, represent only a momentary eddy in the vast flow of cosmic time. Yet it also suggests that intelligence and technology, rather than being unique to our particular moment in Earth's history, might be recurring phenomena that arise whenever conditions are favorable. The philosophical implications of the Silurian hypothesis extend far beyond questions of geology and archaeology. If other technological civilizations have indeed risen and fallen on Earth during the vast span of geological time, this would fundamentally alter our understanding of intelligence, progress, and the meaning of human existence. The possibility that we are not the first challenges the anthropocentric view that places humanity at the center of Earth's story. Instead of being the culmination of evolution's long journey toward intelligence, we might be simply the latest experiment in the universe's ongoing exploration of what it means to be aware, to understand, and to create technology. This perspective might seem diminishing at first if others came before us. Perhaps our achievements are less significant than we imagine. But there is another way to interpret this possibility that is profoundly uplifting. If intelligence and technology have arisen multiple times on Earth, this suggests that these phenomena are not accidents but inevitable outcomes of the universe's fundamental properties. The laws of physics that govern the formation of stars and planets, the chemistry that enables the emergence of life, and the evolutionary processes that lead to complexity and awareness might all conspire to ensure that intelligence arises repeatedly throughout the cosmos. We might be not alone in space or unique in time, but part of a vast community of intelligence that spans the universe and extends across geological ages. The search for ancient civilizations also illuminates the relationship between intelligence and planetary stewardship. If previous technological civilizations did exist on Earth, their apparent disappearance raises urgent questions about the sustainability of technological development. Did they exhaust their resources? Did they trigger environmental changes that made their planet uninhabitable? Did they destroy themselves through warfare or social collapse? Or perhaps they successfully navigated these challenges and evolved beyond the resource-intensive phase of technological development that characterizes our current civilization. Maybe they learned to live sustainably on their planet, developing technologies that worked with natural systems rather than against them, creating energy sources that didn't alter the planet's chemical balance, and establishing social systems that could persist for millions of years. The possibility of successful long-term civilizations offers a vision of what humanity might become if we can solve the challenges that currently threaten our survival. Climate change, resource depletion, environmental degradation, and social inequality might represent temporary growing pains rather than insurmountable obstacles to long-term civilization. The study of our own civilization's chemical signatures provides a roadmap for this transition. The traces we're leaving in Earth's geological record reflect not our greatest achievements but our greatest inefficiencies. The carbon isotope anomaly from fossil fuel combustion indicates massive waste of ancient solar energy stored in geological formations. The artificial isotopes from nuclear weapons testing reflect the application of our most advanced physics to destructive rather than constructive purposes. A mature technological civilization might leave very different traces, subtle signatures of renewable energy systems, evidence of closed-loop resource cycling, and the chemical fingerprints of technologies that enhance rather than degrade planetary systems. Such a civilization might be essentially invisible from a geological perspective, having learned to meet all its needs without creating the dramatic chemical signatures that characterize our current industrial phase. This vision of invisible ancient civilizations raises profound questions about detection methods. If successful technological societies learn to minimize their environmental impact, they might become undetectable using the methods we've discussed. Their success at achieving sustainability might paradoxically ensure that they remain hidden from future investigators. This possibility suggests that the absence of obvious evidence for ancient technological civilizations might actually be encouraging news for our own long-term prospects. If others before us successfully made the transition to sustainability, perhaps we can as well. The silence in the geological record might reflect not the failure of ancient civilizations, but their success at learning to live within planetary boundaries. The question of what ancient civilizations, if they existed, would tell us about ourselves ultimately depends on what we choose to hear. We could interpret their hypothetical existence as evidence that intelligence is common, and that we are part of a grand cosmic community stretching across space and time. We could see their apparent disappearance as a warning about the challenges facing all technological civilizations. Or we could view their potential success at achieving invisibility as inspiration for our own transition to sustainability. Perhaps most importantly, the search for ancient civilizations forces us to think beyond the immediate concerns of our daily lives and consider our civilization from the perspective of deep time. This temporal perspective reveals both the fragility and the significance of what we're creating. Our technologies, our knowledge, and our cultural achievements represent the culmination of billions of years of cosmic evolution. Yet they exist in forms so ephemeral that they could vanish within centuries without leaving obvious traces. This paradox between the cosmic significance of intelligence and its apparent fragility lies at the heart of the human condition. We are the universe's way of understanding itself, yet we exist for such brief moments that our individual lives seem insignificant against the backdrop of cosmic time. The possibility that other civilizations have faced this same paradox and found ways to persist offers hope that our own brief flicker of awareness might somehow continue and perhaps even flourish. The Silurian hypothesis ultimately serves as a mirror in which we can examine our own assumptions about intelligence, technology, and our place in the cosmos. Whether or not ancient technological civilizations actually existed on Earth, the process of investigating this possibility has revealed important truths about our own civilization and its relationship with planetary systems. We have learned that technological activity inevitably leaves traces that can persist for millions of years, that these traces are often subtle and require sophisticated analytical methods to detect, and that the absence of obvious evidence doesn't necessarily indicate the absence of the phenomenon. We have discovered that our own civilization is creating chemical signatures that will remain detectable long after all other evidence of our existence has vanished. Most importantly, we have been forced to confront the temporal dimension of intelligence and technology. Our brief existence in cosmic time does not diminish our significance. If anything, it enhances it. In our fleeting moment of awareness, we have learned to read the language of atoms and stars, to decipher the history written in rock and ice, and to imagine possibilities that stretch across billions of years. The question of whether others came before us may never be definitively answered. The geological record is incomplete, analytical methods have limitations, and the signatures of ancient technological activity might be too subtle or too degraded to detect with certainty. But the importance of the question lies not in finding a definitive answer, but in forcing us to think deeply about what it means to be intelligent beings on a finite planet in an infinite universe. If we are alone in time as well as space, then we bear the full weight of representing intelligence in our corner of the cosmos. Our achievements and failures, our knowledge and ignorance, our wisdom and folly become the universe's only conscious commentary on its own existence. This responsibility is both terrifying and magnificent. If others came before us and will come after us, then we are part of something larger, a continuing conversation between intelligence and the cosmos that transcends any individual species or civilization. Our discoveries add new voices to this conversation, and our failures provide lessons for future participants. Either way, our moment of awareness is precious beyond measure. In the vast darkness of space and the immense sweep of cosmic time, brief flickers of intelligence arise to ask questions, seek answers, and wonder about their place in the grand scheme of existence. We are such a flicker, perhaps the first, perhaps the latest in a long series, but in either case, a remarkable phenomenon worthy of our own wonder and respect. The search for ancient civilizations has taught us that intelligence leaves traces, that these traces can persist across unimaginable spans of time, and that the universe has been conducting experiments in awareness for billions of years. Whether we are the first success or the latest iteration in these experiments, we have the opportunity to shape our own legacy and influence the future course of intelligence in our part of the cosmos. The traces we leave behind will speak for us long after we are gone. The question is, what story do we want them to tell? Will they speak of a species that learned to live sustainably on its planet, that used its brief moment of awareness to increase knowledge and reduce suffering, that found ways to preserve and transmit its discoveries to future seekers? Or will they tell of a species that burned brightly and briefly, before consuming itself and its environment in an unsustainable frenzy of growth and consumption? The choice is ours to make, but the consequences will persist for millions of years. In this sense, we are already ancient civilizations to future investigators who will study our chemical signatures and try to understand what manner of beings we were and what we might teach them about the possibilities and perils of intelligence. The Silurian hypothesis has given us a new lens through which to examine our own existence and our relationship with our planet. Through this lens, we see ourselves not as the masters of Earth, but as temporary participants in a much larger story, a story that may have included other chapters of intelligence and awareness that we are only beginning to learn how to read. Whether or not we were the first technological civilization on Earth, we have the opportunity to be the first that consciously chooses sustainability, the first that deliberately designs its legacy for the benefit of future intelligence, and the first that uses its understanding of deep time to make decisions that honor both our cosmic origins and our planetary home. In the end, the question of ancient civilizations returns us to the most fundamental questions of existence. Who are we? Why are we here? What is our responsibility to the future? The answers we choose to these questions will determine not only our own fate, but also what traces we leave for whatever forms of intelligence may arise after we are gone. In this way, we are all ancient civilizations to the future, and all future civilizations to the past, connected across the vast sweep of time by the precious and fragile phenomenon of awareness itself.